mess up the paper title. Good morning, and welcome to session 6A on synthesis. So we're going to have 5 talks in a session. A couple of them will be remote, and so let's first welcome Ziteng Wang, who's going to tell us from batch to stream automatic generation of online algorithms.
All right. Can you hear me? Okay, nice. Thanks for the introduction. Hi everyone, I'm Ziteng Wang from UT Austin. Today I'm gonna present our work from batch to stream automatic generation of online algorithms. Let's begin with a little bit background about online and offline algorithms here. So offline algorithms are used in a traditional batch processing setting where a large chunk of data was first put into a database, and then they will be processed in a fixed interval and getting some results periodically. On the other hand, online algorithms are used in a stream processing setting where we will process and analyze the data in real time. We'll put it into a continuous data processing stream, and then it will always get us some live result. So stream processing can be useful in some time-sensitive computations. For example, it could be like fraud detection for financial companies, marketing and sales analytics, and finally inventory management, so on. And we see like increasingly popular frameworks that adapting this kind of stream processing like Apogee Spark, Storm, and Flink. Here's an example of an offline algorithm computing simple mean. So here, let's say we wanted to compute the simple mean for 0, 1, 2. And here, we know the answer is 1 because we will first compute the summation s to 3 and over by the length of the list 3. On the other hand, let's say if the list is updated with a new item 3 here, then we will need to recompute the sum and length all from scratch. On the other hand, the online version is a bit different. It has 2 parts, a Python function called mainOnline and an initializer. I'll get into initializer in a second. Let's first take a look at the function signature of mainOnline. So v denotes the value of previous mean, and then n is the number of previously processed items. Finally, x is the new item. So the initializer basically is the value of v and n before we even processed any element in the stream. Say that's the state after processing 0, 1, 2. If we want to compute the new mean when adding 3 to the stream, then we can incrementally do this by first updating new s and then having new n. And here, the complexity of the offline algorithm is O of n because you did a linear scan over the list, whereas the online algorithm will only be a O of 1 because we just update the element, just update one element. So in our work, the problem statement is as follows. The offline program is a program that transforms a list access into a result P of access. And then the online thing will be a bit different. That's something we call online scheme, which is a tuple of I and P, where I is the initializer and P prime is the updater, which is usually something we call online program. But really, we need the initializer to make the online program work as well. Our problem statement here will be, given an offline program P, find an online scheme S, such as P is equivalent to S. And here we have the offline-online equivalence here. Basically says that our output of the offline program should match the outputs of online program when we are doing a fold left over the stream modeled as a list. So what is the challenge here? Well, take a look at this simple example. This is computing simple variance in a 2-pass style. And interestingly, the online algorithm of variance is actually coming from an old paper in 1960s. And this is called actually Welford's algorithm. And if you take a look at the Welford's implementation, it has quite complex nonlinear expressions. To make things even worse, we haven't known anything about like what are the additional states needed here, so we need to figure it out. So in our work, we use excuse me, we have two parts that basically work around these two problems. So Opera will first use a static analysis to figure out a relational spec, and I will introduce that later. And then the relational spec will be helpful in constructing the initializer, and then use compositional deductive synthesis to figure out the online program. Let's start with the relational spec. So here is an example of the same program variance but written in our functional intermediate language. And then here's the relational spec Opera inferred. Here, the relational spec is something we call the relational function signature. It basically consists of two parts. The first part is showing the first column of relational spec, which is the parameters, the function signature of the online program. And secondly, it also says what those arguments actually mean here. So the specification column is exactly what the semantics is. So for example, as is just fold left plus over access. How do we infer the relational function signature? We use a lightweight static analysis to figure out all the offline expressions in the variance program. Offline expressions are expressions that involves the list input as one of its arguments. And then we will figure out like each parameter with its specification precisely highlighted in the program. And since I promised you we can get the initializer, actually we can just get it for free, because we just construct the initializer by evaluating the expression on the empty list for each specification shown here in the relational spec. And you might have a question like, what if I divide by 0 then? Well, we use the notation of safe division that basically all the division by 0 will result in 0. So that's all the zeros we get from evaluating expressions here. So now we have the relational spec from static analysis. We're ready to take a look at how compositional deductive synthesis work. The key idea behind our synthesis methodology is that we can redefine equivalence in terms of equivalence module RFS. And intuitively, that means that an online program P prime preserves the RFS. Then we will say like this is inductive modulo RFS. Let's take a look at the formal definition here. So formally speaking, this is online program P prime is inductive relative to RFS phi if the following Hoare triple is valid. In a high level, that means that if the state variable y has some correspondence to xs, then after getting like a y prime, which is the updated state variable, we should get some correspondence to the new list xs prime. So with that definition, we show that the equivalence can be redefined as follows. So the online scheme S will be equivalent to the original offline program P if, first, its initializer is consistent to the RFS, and secondly, P prime is inductive relative to phi. So we can redefine our synthesis task as given RFS, the relational function signature phi, and then construct P prime that is inductive modulo phi. And since I already tell you like how do we construct the relational spec phi, it's just something we can just figure out like the program P prime. And this reformulation facilitates deductive synthesis. Let's begin with the first part of the learning part, decomposition. So the decomposition idea is based on two observations. The first observation is that offline program and online program share this the same high-level structure. So we can infer a sketch of online program to reuse that structure. Secondly, online expressions are independent to each other. So we can just decompose the online synthesis problem into independently solvable tasks. Well, here's an example of sketch generation. In the same variance program, we just replace offline expressions highlighted here with unknown hosts showing the sketch here. And then the original expression is used as specification. Just to recap, the offline expression is really like the expression that uses the input list access. And now we have a sketch. We can synthesize the expression. The high-level idea behind expression synthesis is that we will replace offline expressions with equivalent online expressions. And here, we will use the deductive synthesis approach to find such equivalent expression. You might recall that the idea is the relational spec enables us to use logical reasoning for sketch completion. So how do we do this? Well, this is based on the following task description. So we wanted to synthesize an expression E prime such that E prime is equivalent modulo RFS to the offline program. So what on earth is equivalence modulo RFS then? It basically means that under the assumption of the relational spec phi, we can have the online expression E prime equivalent to E when we are updating XS to be XS concat X. Here is an example. Let me show you how S plus X is equivalent to the specification for unknown box 1. Left-hand side is easy, just like plug in E prime. And the right-hand side will be, we are having like a fold left plus over XS plus X. So we can use the definition of fold left to unroll one step. And then the specification tells us S plus X is equal to the expression, which concludes the example. The idea behind finding such an E prime is that we can find the implicate of form some program equal to a term where the term is over the online parameters. Here's the concrete example. So phi is the relational spec we inferred from the input program. T is the specification for the synthesis task. A is the definition for fold left instantiated on plus. So we found that the conjunction of phi, T, and A actually implies the online expression. So we are down here, that's nice. However, you might notice that in my formula, there's many like higher order combinators, which could be a problem because we need to encode everything into like a SMT solver in order to find such implicate. So please refer to our paper for the detailed workaround. We use fresh variables to get over this problem. But the observation is that sometimes we cannot find such implicate. So in that case, we will try to under-approximate the implicate, and then we will use some trick to mine useful expressions from the input program. And this mined expression will be useful in later search. By searching over like the template, we can find the final implicate. That's how we combine symbolic reasoning and search. So finally, how well does our technique work? Well, to answer this question, we collected 52 programs from 2 sources, statistics and auctions. So the statistic benchmarks comes from popular GitHub repositories, SciPy and OnlineStats.jl, and there's examples like skewness, variance, geometric mean, and auctions are those programs from a popular benchmark suite called Nextmark for stream processing applications. Example including like generating bidding reports, monitoring new bidders, and so on. Here we studied the AST size of those programs in these 2 categories. For statistic functions, you have like a significantly larger online program due to the complexity introduced by cubic and quadratic expressions. But for auction programs, they usually stay relatively the same. Okay, so we evaluated Opera against 2 baselines, CVC5 and Sketch. Those are the state-of-the-art Saiga solver with nonlinear arithmetic support. As you can see in the plot, Opera synthesized 50 out of 51 online schemes within an average of 25 seconds running time. And it significantly outperforms the existing baselines here. And we studied two ablations here. The first one is opera no decomp, where we just turn off compositional synthesis technique. And the second one is called opera no symbolic, where we disable symbolic reasoning technique and then but keep like decomposition thing on. And here's the result. As you can see, disabling either of these key techniques will have a significant negative impact on opera's performance. So that is opera, and I'm really excited to give this talk as this is my first talk. Thank you so much. And I'm happy to take questions.
Questions.
Yeah.
So if I understand correctly, the online algorithm you synthesize is prepend an element to a list. What if I want an algorithm that's append an element to a list? Will your approach still work?
So the question is, right now, our problem statement assumes that the stream setting will always append like the element at the end. So will it work if I just insert anything at the beginning? I think,
Yeah, or the other way around.
yeah, exactly. Okay. I think this question is really asking like whether this same technique can be used in some general incremental computation scenario. Yeah. Because in a streaming problem statement, you always put the item at the end. So I think probably we need some adaptation to say, to make the thing work. But I can imagine in some incremental computation scenario, there might be still some relational specification needed. So in that case, if you have some relational specification, we might be able to like reuse some of the technique. And I don't think there's fundamental reason that prevents you from doing this.
Okay, so another question that you extract some auxiliary values by a statistical analysis. I'm wondering, is there some completeness guarantee such that for any algorithms, for any online algorithms, it's enough to just use in this set of auxiliary values?
That's a really good question. So the question is whether our static analysis thing will impact the completeness of our algorithm.
Yeah.
So I think it can be viewed as this. So our approach is really like putting any information you might needing from the offline program into like the state variables. So in that sense, I think we are really like saving everything we potentially needed. And we always only remove something if in the synthesized program, we ended up not using any of them. So in that sense, I think you're still having like the complete information you may have. Okay. So in that sense, I think it won't affect the completeness issue.
Okay.
Does that answer? Yeah, thank you.
Hi, thank you for the nice talk. So my question is about the sort of distributed setting. So in your setting, you're synthesizing the update function basically on a list processing program. Have you thought, so if you're doing something like synthesizing like MapReduce programs, you might also want this update function to satisfy something like some sort of commutativity, associativity properties. Have you thought about if your approach generalizes to that setting?
Yeah, that's right. I think there's definitely like something we can do, and actually we are considering of like expanding the problem statement to be more like a parallel computation or divide and conquer style computation. I think in that sense, since again like stream processing thing is still a very like specialized and restrictive form of both incremental and parallel computation. So I guess right now I don't have like many insight about this, but definitely this is an interesting and challenging direction that I'm eager to explore.
Okay, thanks.
Yeah.
That was a wonderful talk. Thank you. One thing I was curious about is in some of your first examples, you had these like explicit for loops in your inputs, but then in the later ones, your RFSs just included these higher order combinators. I was wondering if you had support for like these for loops as part of your RFS.
Oh yeah, that's a fantastic question. So right now, we take Python programs with imperative loops as input, but we have like some rule-based translation to basically translate that Python program into higher order combinators. And in principle, I think it's possible to basically translate with some existing work about transpiling imperative to functional code. But right now, since our application scenario is very restricted to the streaming application, our rule-based translation is applicable on our on the benchmark side, and yeah, I think right. You can definitely handle that.
Great, thanks.
Yeah.
Hi, great talk today. It was
Thank
very
you,
clear.
Nadia.
Thank you. So my question, I think, is a follow-up on Yingfei's question on completeness, really. So I think, so my question is, what is the class of batch programs that this would actually work on, right? Because in all of your examples, these offline expressions that you're replacing, they're themselves folds. They were all folds, right?
Yeah.
And it feels like that is maybe the key to why these intermediate values were the only ones that you needed, right? And you could actually reproduce in this online fashion. Or am I wrong? Or maybe you can give me an example of a program where this is not applicable.
Right. So I think to answer that question, it can be answered like in two. Okay. So sorry. Let me repeat the question first. So right now it seems like all the programs are written in some fold left form, and this is in like a functional. So it's really could be kind of my technique could be specialized for this program, and well. It can be answered in two ways. So first, whether the language, the functional IR is expressive enough. So in practice, when we collect the benchmark, we don't have like the functional IR in mind. So we just like collect all the benchmark we can have from those two categories. And in practice, we found that we can always express that in this functional IR. And secondly, there's a publication in functional program that basically discuss the expressiveness of a small calculus with a fold. So it looks like the language should be expressive enough.
Mm-hmm. But for example, if it was a quadratic program in the first place,
right? So we
cannot do it, right? I mean.
Sorry, could you clarify like what is the quadratic program?
Well, like if the batch program had to go over the list like quadratically a number of times, it seems like it would not work, right?
Well, because like for example, if the input stream is like a stream of lists. Is that what you're asking? Like it's no longer like a numerical.
We're sort of out of time. Can we take that offline? Yeah, sorry.
Okay. Thank you.
Okay, while we're getting set up, our next talk is decomposition-based synthesis for applying DNC-like algorithmic paradigms, and Rui Ji will be our speaker.
So, okay, great. So, yeah, thank you for the introduction. And hi, everyone. My name is Rui, and I'm super excited here because I will have 2 slots to introducing our recent work on synthesizing efficient algorithms. Yeah, so we will have a lot of time on this topic. Yeah, and at the very beginning of these 2 presentations, I would like to introduce our whole group at Peking University working on this problem. Our final goal is to automatically synthesize efficient programs that may require complex optimizations, such as algorithm-level optimizations. Yeah, and we have several people working on it, and we have also received many help from our excellent collaborators, such as Nadia. Should be. Oh. Okay, so and we have made progress from different aspects. For example, we have constructed a dataset including many interesting and also challenging problems. We have designed many synthesizers for different kinds of complex algorithms, and also we are working on a verifier to automatically verify our synthesis result. So although in these 2 presentations, I can only introduce the progress on synthesis part, but if you are interested in any point on these slides, yeah, let us just discuss later at any time. Okay, so let's move to the main part. So in my first presentation, I will show you how to efficiently synthesize divide and conquer algorithm. So let me begin with a question. So please raise your hand if you already know divide and conquer before stepping into this room. Okay, great, excellent. So we have many experts on algorithms, so it will make my presentation much easier. Yes, thank you so much. Okay, so basically, divide and conquer is a very classical algorithm to evaluate some function on a list. It suggests that we can first divide the input list into 2 halves, then recursively apply the same function to the half lists, and then somehow using some magic combinator to combine the sub-results together. The key advantage here is that the two recursive calls can be distributed to different processors. That means that any divide and conquer algorithms, in theory, can be run efficiently in parallel. Okay, so this is the overall procedure of divide and conquer. Pretty simple. But the problem here is that writing a divide and conquer algorithm is not that easy. The problem is this combinator can be pretty complex even for very simple problems. So it can still be a significant challenge for the programmer to write this. To see this point, let us consider a very concrete problem that is second minimum, which our goal is to calculate the second smallest value from an integer list. So solving this problem is nothing difficult, right? We can just write this program by sorting the list from small to large and then taking out the second value in the sorted list. So I believe that every programmer is willing and is able to write such a program. Okay, so now the problem is that let's consider what will happen if we want to write a divide and conquer algorithm. That is, how can we get this combinator? Intuitively, this combinator should take the recursive results as input, right? The second minimum of the half lists, and it should produce the corresponding output on the whole list. Yeah, so this is clearly an input-output specification for the combinator, and one may use it for synthesis or for reasoning. But the problem here is that such a simple combinator usually does not exist. For example, in this case, we know that the second minimum of the half lists are in fact not enough to determine the whole second minimum. For example, suppose the left list is 1, 3, and the right list is 2, 4. Then the combinator can only know 3 and 4 in its input. But it is expected to produce that value that is unknown for him, that is the value of 2. So clearly, the information here is not enough for such kind of combination. Okay, so what we can do if we want to manually apply divide and conquer? So we need to supply more information to the combinator. So one solution is that we can introduce some auxiliary value. For example, we let the divide and conquer algorithm not only calculate the second minimum, but also calculate the first minimum. Right? So in this way, we have much more information, and then, as we can see, the missing value 2 now appears in the input. Okay, so this is how we will manually apply this divide and conquer algorithm. And the problem here is that now with the help of auxiliary values, there are many, many more inputs to the combinator, so that it will just make our combinator even more complicated. So the content of this combinator is not important, but we can just compare it with our initial program of second minimum. So clearly, the combinator is much longer and involve much more low-level computations like branches and comparisons. So it would be definitely great if we can automate this procedure. That is, automatically synthesize this combinator just from a user-provided arbitrary reference program. Okay, so this is our motivation. And later in the remainder of this slide, I will first show you the formal definition of our synthesis problem, then the basic idea of our approach. Then I will show you some interesting extension of our approach beyond the divide and conquer. And at last, I will show a very brief evaluation. Okay, so the synthesis problem. So of course, our synthesis problem is about synthesizing divide and conquer algorithms, right? So our input is a reference program provided by the user denoting the program they want to write into divide and conquer. And the most important synthesis target is the combinator that can merge the sub-results during divide and conquer into the whole result. But as shown in our previous example, sometimes we still need some auxiliary values, so we need to introduce another synthesis target, aux, to help us specify those needed auxiliary values. And in the specification, what we want to do is to ensure that this combinator can correctly merge the results. That means that for any possible left list, any possible right list, then given the left result, the right results, the combinator should be able to correctly produce the whole results. So if we unfold these results, the left thing should be the reference output on the left list, auxiliary value on the left list, and the right thing should be these two values on the right list, and the whole result should be these two values on the concatenated list. Okay, so this is clearly a synthesis problem. And you know this problem must be difficult, or otherwise solving it won't be a presentation here. So in more detail, the challenge comes from two aspects. So first, as shown in our previous example, this combinator can be pretty complex even for simple problems. And in our data set, it can be even more than 100 ASD nodes, which is pretty large for program synthesis. And on the other hand, this specifications form is not so simple. It includes 2 unknown programs, and it is in fact relational. So as far as we know, there's no existing synthesizers that can support such a large-scale relational synthesis problem. Okay, so how can we solve this challenge? Our key idea is try to decompose, which is pretty close to the previous presentation here. So our key idea is that somehow maybe you can use some rules to decompose those whole synthesis problem into a series of subtasks, each with simpler form. On the one hand, we can reduce the synthesis scale because in each subtask, we only need to consider a subprogram of some synthesis target. And on the other hand, the specification becomes simpler because in each subtask, there's only one unknown program involved. So this is just a high-level idea, and I will then show you how we can do this decomposition. So following this line, we propose our approach, AutoLifter, that incorporates a bunch of specialized decomposition rules for such kind of specification. And now I will just show you the most interesting one, but there are several else in our paper. Okay, so this decomposition rule, we name it as variable elimination because it can eliminate one variable from the specification. So it is based on 2 observations. First, as we can see, our original specification itself is already in an input-output form for the combinator. And these input-output expressions can both be regarded as functions related only to the auxiliary function, the left side list, and the right side list. So they can be just regarded as input and output generators for this combinator. And let's see what we can do with these two generators. So we can just consider several concrete lists, left list and the right list, and then put them into these generators. And then they will provide some symbolic input-output pairs for the combinator, right? And these inputs and outputs will only be related to the auxiliary function. And because there are many, many different input lists in the world, so we can just get such kind of input-output pairs, and as many as we want. So, and following is our second observation, is that whatever this combinator is, it is always behaves like a function, right? So it can only map the same input to the same output. So let us try to write this requirement down. It means that for any 2 pairs of left list and right list, whenever the output of the input generator is the same, then the result of the output generator should also be the same. So clearly, this is a specification for the auxiliary function, and here we can see the combinator disappears. So we can use this spec to do decomposition. What we need to do is to first synthesize the auxiliary function from its own specification, and then put the result inside the whole one, and then we will get a separate specification again for the corresponding combinator, and then we synthesize it. So a more interesting thing is that both these subtasks are much easier than the original one. First, for the first subproblem, we can just synthesize it by bottom-up enumeration in most cases because this auxiliary function is pretty small. The key reason is that we do not need to be efficient. We only need to be correct to specify those auxiliary functions we need, auxiliary values we need. And for the second subproblem, so it is a very standard program by example task, right? So it is in an input-output form, and both the input and output are known. So we can just extract out many concrete input-output examples and let existing program by example solvers help us solve everything. Okay, so this is the overall idea of the decomposition. And you may have already found that this procedure, in fact, does not use maybe not many specific properties of divide and conquer, right? We do not need to use the property that here is at least a concatenation, and there are 2 lists, and so on. So what does it mean? It means that we can generalize our approach to many other different similar problems. So we find that even though our approach is just designed for divide and conquer, it can in fact be generalized to many other different paradigms, for example, the streaming algorithm mentioned before, and also many specialized paradigms for some specialized problems like the longest segment problems and the specialized data structure, namely segment trees. All of these paradigms, their application problem can be reduced to a core synthesis problem with a similar form where our approach and our decomposition rules can still be applied. For example, let us consider the case of streaming algorithm. So its key idea is to treat the input as a stream and then calculate the value we want just from using a scan from left to right. And in each step, what we need to do is to locally compute the new result using the previous result and the new element we visit. So, and of course, similar to the divide and conquer case, sometimes we need to introduce some auxiliary values to enable such kind of combination. Okay, so we can write this specification down. So the specification here is that for any previous list access and for any new integer, given the previous input of the combinator, then the output should be the new reference output and the new auxiliary values. So, and here is the specification of the divide and conquer. As we can see, they're almost the same, right? Both of them are in the input-output forms for the combinator, and they are both related to two different functions, the combinator and the auxiliary function. So that means that at least the variable elimination you have seen can be applied here, and in fact, our whole approach can be applied. So in our paper, we formalize this whole problem as an abstract synthesis problem, namely lifting problems, and we demonstrate that our whole approach can be applied to this more generalized problem. Okay, so let's end with a very quick evaluation. So in our evaluation, we consider all these paradigms we mentioned before, and we collect a data set from previous related studies and also a website, namely codeforces.com. It is an online platform for competitive programming, which is a context for writing complex programs and efficient programs. And our data set including some classical problems like maximum segment sum and some like bracket matching. And also we include some real problems in real competitive programming. And our results just show that AutoLifter is effective in solving these problems. It can solve most tasks using within a small time frame, and this performance is better than previous related approaches. Okay, so this is everything about these slides. So what we want to do is to automatically rewrite a reference program into a divide and conquer algorithm. And also we notice that our approach can be generalized to other similar algorithms. And targeting at this problem, we propose our approach, AutoLifter, which key idea is to perform decomposition to simplify the synthesis problem, to reduce the synthesis scale and simplify the sophistication. And that's all. So thank you for listening, and I'm excited for the questions.
Hi, I just had a quick question about when you synthesize the auxiliary program, is there any backtracking involved? Like, is the auxiliary function that you synthesize guaranteed to be the right one?
Yeah. That's a very great question. So actually, in theory, this procedure need backtracking because this specification for aux is not precise, right? Because in most cases, we want an efficient combinator, not an arbitrary function. And we do not have any such kind of ensure in the derivation of this separate specification. But an important theoretical result in our paper is that we find that this kind of decomposition is extremely effective in a special case that is divide and conquer producing scalar values. So in that case, we do not need any backtracking. We can solve almost all the problems we have ever known, and we also prove some theorems to justify this observation. Yes, so in theory, maybe we need backtracking, but in our current implementation, we do not have any of them.
It was a wonderful talk. Thank you. It seems like your approach for the divide and conquer makes like a lot of sense, and I can see how that would solve divide and conquer. And I'm curious why you only got not only, but you got the 82 out of 96 examples from your benchmark. Like, what is causing those last ones to fail, given how well matched this algorithm seems to that problem?
Great question. So the problem is that, because in fact our approach just decompose, it does not solving the whole problem from the scratch. It just decompose the problem into some similar form and then pass it into existing synthesizers, right? We use enumeration synthesizer to synthesize the aux, and use existing program by example solver to synthesize the combinator. And here, one problem is that it is just a challenge mentioned by Ziten. It is in some cases, the combinator will involve some complex non-linear operations, which can be pretty challenging for existing program by example solvers. And that's, I think, accounting a major part for the tasks we fail.
I see. So very quick follow-up. Like, if you manually looked at those decomposed problems yourself and you were the program synthesizer, could you slot yourself into the algorithm and solve it? Or is there some fundamental limitation where no synthesizer could solve it? Sorry, you mean the complex combinator or which one? Yeah, we can take it offline maybe.
Okay, great.
Yeah. Thanks.
Thanks. Very, very nice talk. I have a question about how do you deal with this recursions? Is your combinator a recursive program? And by the way, I have another question. Is that I think as this auxiliary values very similar. I would say in the field of inductive environment or loop environment, some program cannot prove by a simple specification. You need to strengthen it.
Yes.
Is there some connection of it?
Yes, I feel they have some connections. So in fact, our auxiliary function can be regarded as an invariant for the divide and conquer, right? It specifies in each single step of divide and conquer what the input is and what the output is. So it can be regarded as an invariant. And for the recursive combinator, so currently we only consider scalar expressions for the combinator, so there is not any recursions. Yeah, and we have also noticed that the auxiliary function we synthesize can be maybe useful for the verification part, which is our another work. Okay.
Since we have a minute, I'll throw in a question too. I was wondering if you had done anything like taking your freshly synthesized divide and conquer programs and executing them. You know, now you can parallelize them. And if you do that, do you now get faster code than the original algorithm?
Yeah, sure. So on the one hand, in our dataset, the input program, because our approach does not need the reference program to be, for example, linear time or to be efficient. So in some problems, the reference program just run in quadratic or triple times. And in that case, our synthesis algorithm is ensured even run in sequential, it is still linear time. So in that case, it is much faster.
But I mean, did you measure? I mean, in how many out of 81 or whatever cases?
No. But I mean, in theory, we can ensure that we can achieve linear speed ups in many. Yeah, but it depends on different libraries of parallelization and depends on the device. Yes.
Great. Okay, let's thank our speaker. Okay, our next speaker is Rui again. This talk is superfusion, eliminating intermediate data structures via inductive synthesis.
Oh, wait. Okay, great. Well, so hi everyone. My name is Rui, and nice to see you here once again. Let us just continue our topic on synthesizing efficient programs. And I'm pretty excited because I'm going to show our most recent approach and also more interesting approach in this topic. So different from the previous work, which starts from a small point that is a very specific algorithm, namely divide and conquer. In this paper, we tackle a more general behavior of optimization, that is eliminating media data structures, and get a different approach. But at the end of this slide, I will show you that, in fact, our new approach can capture all the problems we mentioned in the previous slide using some interesting construction. Okay, so let's just begin. So to begin with, let us choose a pretty different story to separate from the previous slide. So to begin with, let us just consider two important properties that we want to have when writing programs. They are simplicity and efficiency. On the one hand, we want our code to be simple because we want a low cost of coding and maintaining. And on the other hand, we of course want our code to be as efficient as possible because it means a high practical performance. But what is the problem? Problem here is that these two properties are conflict with each other. To see this point, let us consider a very concrete task, namely maximum tail segment sum. The input of this task is an integer list with some possibly negative integers, and our goal is to select a proper tail segment and maximize the sum of all values in this tail segment. For example, here, the best choice is to select the last three integers, and the corresponding sum is equal to 4. So just similar as the previous slide, solving this problem is nothing difficult. So we can just write this simple program following the natural language description of this task. What this program does is to first generate the whole list of all possible tail segments and then convert it into a single a one-dimension list including all possible tail segment sums and then take out the maxima. Okay, so this program clearly simple. So it is short, easy to write, and easy to understand. But its problem is that this program is not very efficient, right? It takes a quadratic time, which is not very good when the input list can be pretty long. So if we go to analyze this program, we can find that this efficiency is in fact caused by the huge intermediate data structure constructed by this tails function. This data structure, its size is already quadratic, making the subsequent calculation at least quadratic, because we should at least scan over this whole intermediate data structure. So given this analysis, it means that if we want to get a more efficient program, we should at least compress this intermediate data structure into some smaller version. For example, a constant number of scalar values. And in this way, we can avoid the bottleneck of the simple program, right? Because we can greatly reduce the cost of scan over this intermediate output. So following this line, we may get an efficient program for this problem. And in this program, we totally rewrite this tails function to just return two integers. The first integer is the value of the MTS, and the second is an auxiliary value equal to the sum of all values in the input list. So when running this new tails function, it will first go inside and go recursions. And in the basic case, when the input list is empty, it will just return two zeros according to its definition. And then it will go back and update this result step by step. In each step, it will first calculate the new sum and use the new sum to update the value of MTS. For example, here, the new sum is equal to 2, which is greater than the previous MTS, so the new MTS will be the new sum. And also, if the new sum is smaller than the value of MTS, it won't change. So, and in this way, we can correctly compute these two values during only a single recursion. And then the subsequent problem becomes much easier. Because we only have two integers returned, what we need to do is to just use a very cheap projection operator and using constant time to take out the value we want. Okay, so this is what we can do to optimize this optimize the simple program. And as we can see, the new program is much more efficient, which is good. But it also has its own problem, right? It is no longer simple. It is much longer and needs some human intelligence to design a proper tails function. So here is the conflict. So as we can see, in most cases, we can easily write a simple program, but it's always, or maybe in most cases, inefficient because of intermediate data structures. And also, if we are willing to pay some efforts, we will be able to optimize it into an efficient program, but such a program is usually non-trivial and never simple. In this paper, we want to do something with this conflict. So what we want to do is to use program synthesis techniques to reconcile these conflict properties. In detail, we want to just come up with an optimizer that can automatically eliminate intermediate data structures, then transform from the simple program to the efficient program. And in this way, the user can feel free to write the simple programs, and there will still be an efficient program for the runtime performance. Okay, so following this goal, we propose our approach, SUFU, which uses inductive program synthesis as the backend to eliminate intermediate data structures. And this very good name, SUFU, comes from the abbreviation of two related lines of research. They are super optimization, which uses inductive synthesis to optimize programs, and fusion, which first studies the general idea of eliminating intermediate data structures. Okay, so in the remainder of this slide, I will first show you an overall workflow of SUFU, and then I will show you two very interesting applications of our approach, and finally end with some very brief evaluation. Okay, so the input of SUFU is a reference program which we suppose to include some intermediate data structures. And SUFU also needs a type-level annotation to specify those intermediate data structures to be eliminated. We call it packed data structures. And then given this information, SUFU will first go a round of type-level analysis and then extract out all those expressions that are related to the packed data structure. For example, here, there are three such kind of expressions. There are two constructions happens in the function of tails, and also one consume, which consumes the constructed packed data structure into the final value of MTS. Okay, so after get this analysis result, so we know that our final goal is to eliminate this intermediate data structure in the final program. So it means that all these three expressions should no longer exist in the resulting program, right? So SUFU will just treat it as sketch and then synthesize to rewrite all these extracted expressions with scalar expressions. And in this way, there will be no longer packed data structure exists in the resulting program, and in our case, we will get the efficient version of the maximum tail segment sum problem. Okay, so this is the high-level procedure, and the key problem here is that how can we solve this sketch problem, right? Because, I mean, the optimizer program is usually complicated, so we face a significant scalability challenge. In our data set, these new expressions can be even larger than the previous paper, which is a very monster size for a general purpose sketch solving. Okay, so how can we solve this problem? let us consider an ideal world that we can get separate input-output examples for each sketch hole. Then at this time, we can find that we no longer need to consider the auto sketches, and then we can use program by example solvers to synthesize these expressions one by one and separately individually. So now the scalability challenge is solved, right? Because we have many effective program by solvers can synthesize very large scale scalar expressions. So this is also the secret sauce of Sufu. So Sufu will use a series approach to extract out separate input-output examples for these sketch holes and then pass them to existing solvers. To achieve this, Sufu will first synthesize a helper function, namely we call it a compression function, and then use this compression function to generate examples. And intuitively, this compression function just specifies how we will compress this packed data structure into the final program, into the final version. For example, we know that in the reference program, the packed data structure is the list of all possible tail segment sums, all possible tails. And what we need to do is to compress it into two integers, the value of MTS and the value of sum of all, and the sum of all possible values. So the expected compression function here should take the left side list as the input and then correctly produce the corresponding two integers on the right. So later I will first show you how this compression function helps generate input-output examples, and then I will go back to the problem of synthesizing this compression function. So for simplicity, let us just consider the third sketch hole and recall that our final goal is to rewrite this sketch hole with some scalar expression while keeping the global input-output behavior of the whole program unchanged. So what we can do here? We can first generate a bunch of random inputs and run the sketch program, and meanwhile we keep the track of the whole execution procedure and record all input-output pairs of the original expression here. For example, in this case, we will know the original expression maximum epsilon TS will produce value 1 when given this nested list for TS. Okay, so because we want the global input-output behavior unchanged, so an intuitive idea is that maybe we can just use these input-output pairs as the input-output examples of the new expression. But here is a gap. So because in the collected input-output pairs, there may be some packed data structures which no longer exist in the resulting program. But our compression function can help us bridge this gap. So because the compression function just declares how we will compress each packed data structure, so what we need to do is to just apply the compression function to each involved packed data structure, and then we will get a very concrete input-output examples for this separate sketch hole. And then the later problem is for the program by example solver. Okay, so this is the overall example generation procedure. And it looks pretty effective. And the only problem remaining is that how can we know this proper compression function before synthesizing these sketch holes? Okay, so recall that the only role of this compression function is to generate input-output examples for the new expression or the new sketch hole. So of course, we want the later synthesis procedure to succeed, right? Or otherwise, the overall optimization procedure will fail. So it means that this compression function should at least ensure a realizable program by example task for the new sketch hole. That means that there should at least exist some program that's satisfying all input-output examples collected. So to synthesize from this specification, as we can see, our previous idea of variable elimination in the previous presentation will help. So here, this specification is in an input-output form, and also we can see that this new expression, whatever it is, its input-output behavior must be a function. So again, we know that this function must map identical inputs to identical outputs. So by writing it down, we get a specification of the compression function, and we can just synthesize it by bottom-up enumeration. So this is the overall workflow of Sufu, and so it first uses this specification to synthesize a proper compression function, and then feed it to extract out input-output examples, and then separately synthesize each sketch hole by program by example solvers. Okay, and then so there are also many details remaining, but let us just pause that here, because I want to use the next several minutes to show you two very interesting applications of Sufu. So the first application is just our topic in the previous slides. That is how to automatically apply some algorithmic paradigms to rewrite some reference program. So with the help of the Sufu as the backend, we can write a magic function called apply divide and conquer, which can help which intuitively can apply as applied divide and conquer algorithms. Whenever the user want to rewrite some part of their code to be divide and conquer, they only need to apply this magic function to the function they already implemented. And then Sufu will help them generate the very specialized and very efficient divide and conquer algorithm. And the magic thing here is that the user does not need to know anything specific about Sufu and divide and conquer. And in this interface, there is even no packed annotation exist. So what is the secret here? So it is, in fact, pretty simple. So the core of this function is a template of divide and conquer, which only calculates the identity function. So as we can see, every time when we split a list, it will just concatenate back the recursive results. So that means that this function will always map any input list to the identical input, to the identical list. And then given the reference program, this function will just compose this reference program with the template function and then mark this intermediate data structure here as packed. So let us consider what will happen if we apply Sufu to eliminate this intermediate data structure. So at first, during the elimination procedure, this function divide and conquer can no longer produce this whole list, right? Because they will be compressed. So it will force it to directly calculate the final output of the reference function and then resulting in a very specialized divide and conquer algorithm for this reference function. So with a similar construction, we find that any paradigms we considered in our previous work can correspond to some applied functions constructed in this way. So that means that Sufu can solve all of these problems. So so in other words, Sufu is strictly more generalized than our previous work, AutoLifter. And another very quick application is that Sufu can also be applied to synthesize some interesting native interpreter for simple DSLs. So suppose that we have a host language where we know everything. For example, we already know the interpreter of this function, of this language. And one day we constructed some DSL over this host language using some syntax sugar, and which means that we will know a desugar function from the DSL to the host language. And what we can do here is to compose this desugar function and the interpreter, and then mark the intermediate program in the host language as packed. And then Sufu will just help us eliminate it and generate a native interpreter just from the DSL directly to the values. OK, so let us end with a quick evaluation. So in our evaluation, we consider 3 sources of benchmarks from previous work of Fusion and also 2 datasets in the context of program synthesis, where recursion is from a dataset of synthesizing recursions, and the divide and conquer is just our previous dataset for synthesizing divide and conquer and similar algorithms. And our evaluation results shows that Sufu is pretty good at solving these problems. It can solve almost all, most tasks. And also compared with sketch solvers, Sufu is much more effective. And also even compared with specialized approach for some of these solves, Sufu can even solve a competitive number of benchmarks or even a more number of benchmarks. OK, so let's end with a summary. So this work is motivated by the conflict between simplicity and efficiency, and we want to use program synthesis to help us eliminate intermediate data structures, and in this way reconcile this conflict. And our approach to Sufu takes a reference program as input and also some type-level annotations, and it can help us automatically generate an efficient version without these data structures. And we have seen 2 interesting applications of Sufu, which can be used to apply paradigms and also can be used to synthesize some simple interpreters. And now you can try Sufu very easily just through this IP address or scan this QR code. So if the server down now, I will try to fix it within 10 minutes. Okay, hopefully it is not the case. And so thank you very much. My name is Rui, and I'm so glad that I can give these 2 talks here. And I'm very excited for the questions. Thank you.
I have one question to the 3 previous talks. So that's very efficient, isn't it? So 2/3 of them to you. So some of these synthesis problems are reminiscent. You basically have an incremental problem, which is like you have a function and somebody changes the input.
Yes, exactly.
And there's a lot of techniques that have been explored, and exactly. That go back to the 20th, 19th, and actually 17th century.
From the community of Fusion, right?
Pardon?
Fusion and incremental computation.
Yeah,
and so on.
incrementalization and find a difference from a differentiation. There you have you have you compared what can be solved by these algorithmic techniques, because many of the examples that I saw, at least here, would be amenable to that.
Yeah. So we have explored some of the previous approach, and one motivation for us to use inductive synthesis is because we find that previous approach mainly use some, for example, program level transformations or some syntax level predefined transformations, and they are not so good as those complex problems that may require imposing some auxiliary values, because these auxiliary values depend on specific problems and they can hardly be captured by predefined rules. So in this paper, we just consider to reformalize this whole problem as an inductive program synthesis problem and then solve it efficiently using our approach. And also we have some evaluation results in our paper that show that our approach can solve more problems than previous fusion approach, which based on syntax level transformations. Yeah.
Have you compared against the kids and the RAP systems from the 1980s? Probably not, because they don't exist anymore.
Yeah, okay. We compared with a pretty recent fusion system that is about.
RAPS is automatic. Well, it doesn't exist.
Yeah. But we can try to explore this approach later after. Yeah. Thank you.
Just a quick question. I was wondering, how did you get the signature for the new one? It was like an int tuple of ints. I didn't see how you got that. Was that something that the developer annotates, the pair of ints?
You mean the signature in the final program, right?
Yeah. Is that something that the developer puts?
Yes, this is exactly the output type of the compression function.
But the developer writes int.
No. This is just rewritten by Sufu.
Okay.
So the whole write program is generated by Sufu, and Sufu will also rewrite this packed necessary list into int times int. So it is not.
So you also search over the set of possible output types? Because how do you know that?
Yeah. This is because during the synthesis of the compression function, we will have a bottom-up enumeration to synthesize it, right? And this bottom-up enumeration does not limit the output type into a very specific type. It can be any scalar type. For example, it can be int, can be boolean, can be pairs of int. And then once we find a proper compression function satisfying our specification, then this output type will be the resulting type of this packed data structure.
Okay, I see.
So let's do one more, but please try to make it quick.
Yeah. Thank you for the amazing talk. I just have a quick evaluation question. So I know Farzan et al. Has a few papers on divide and conquer synthesis, right? So I wonder if that is in your benchmark.
We compare it with Autolifter, our previous approach.
I see.
Yeah, and we just find that, of course, first our approach requires less inputs than that approach, right? That approach requires single pass programs, and single pass programs itself will involve some auxiliary values. And on the other hand, the number of tasks we solved is competitive with their approach. Yeah. You can find the detailed result in the Autolifter paper.
Great. Let's thank our speaker again. Okay, our next talk is going to be remote, so we'll for this to get page down.
Oh, should I start? Do I start? Everyone hear me?
If you haven't been to one of our remote talks before, this will go as normal, and then we'll ask questions afterwards, just as if the presenter was here. Great. Okay, our speaker is Kuntan Han from Stanford, and the talk will be on recursive program synthesis using paramorphisms.
Right. My presentation today is about a stochastic program synthesis project I started with Alex. We've had some remarkably exciting results, to the extent that it's surprising to us that it even works. We're still exploring ways to generalize its success. For today's talk, I'll first introduce the smooth problem and prior work.
At the moment, we're just working on it.
Those Can everyone hear me now?
I'm afraid we still can't hear you.
You all can't hear me. Wait, I think in the how about now? Hello?
Could you just try saying something for a second, please?
Check.
There we go. We've got sound. Fantastic. All good. I think we're ready to go.
Okay, let's start. Hi everyone. My presentation today is about a stochastic program synthesis project I started with Alex. We've had some remarkably exciting results, to the extent that it's surprising to us that it even works. We're still exploring ways to generalize its success. For today's talk, I'll first introduce the synthesis problem and prior work, talk about what we have achieved and how we achieved it. Then I'll leave some time for discussion. Now let's talk about some prior work. There has been substantial interest before in the programming by example problem. Most prior success has been focusing on domain-specific languages, in which case it's possible to develop data structure that will represent the semantics of a large class of programs. For example, synthesis systems have been developed for language with a few primitive string operations, a subset of SQL, and graphical programming languages. This synthesis system has some notable common characteristics. The task is domain-specific. The language is first order, and they do not deal with complex control flow. These systems have developed very efficient data structure and algorithm for those specialized tasks, much more efficient than exponential search in the space of programming terms. However, it's usually difficult to generalize this algorithm to general-purpose programming. It's not surprising that synthesizing general-purpose programs is much more difficult. Maybe the single most important feature that distinguishes general-purpose languages from domain-specific languages is recursion. There has been some success by limiting the scope to data transformations. For example, a recent paper employs conflict-driven cluster learning to synthesize first-order programs that uses list processing combinators. The combinators themselves, including sort, reverse, take, sum, etc., are recursive functions, but the programs to be synthesized are not explicitly recursive and rely on these combinators to perform recursive computation. One interesting instance in the space is lambda square, which uses some similar ideas as an system. including the use of high-order combinator. We include this system in our comparison. Finally, the goal of general-purpose programming synthesis is to directly synthesize recursive functions with explicit recursion. This has turned out to be difficult for deduction-based synthesizers because we might not even know the semantics of a function when we need to synthesize or call it. Early system requires so-called trace completeness to work around this issue. Basically, input-output examples have to include example for all recursive calls, which is a serious limitation. Some later systems elevated this issue, but according to our test, they are still sensitive to the choice of examples and can at most synthesize simple functions with one level of recursion. What does one level of recursion mean? For example, Smith and Child, two of the prior state of art, can synthesize multiplication if you provide addition as a library function, but if you provide just zero and the successor function, this problem is out of their reach. Now let's talk about some results. First, let's look at some numbers. We have assembled a suite of 15 synthesis benchmarks for functional programs from previous Smith benchmarks, the Haskell prelude library, and the Haskell data.list library. We tested the system on randomly generated example to test the sensitivity to the choice of examples. There are 55 out of 59 benchmarks, significantly outperforming previous systems. Notably, Parallel benefits significantly from parallelism. We are showing performance of Parallel using 8 core in the first column and single core in the third column. Parallel speeds up almost superlinearly and solves more problems. This is because Parallel's underlying stochastic search algorithm is both embarrassingly parallel and benefits from concurrency, which is a distinct feature when comparing with previously deduction-based systems. Now let's look at some progress Parallel has synthesized. Our synthesizer Parallel can successfully synthesize significantly larger and trivial problems when comparing to parallel systems. Let's look at a similar example, the factorial function. As the first assignment of many functional programming courses, it is not that complex. However, think about what if you're asking someone who don't know multiplication and addition yet, and knows only about inductive definition of natural numbers, maybe some first school student in France. Moreover, what if you don't know what is factorial either, and you are only provided with the first few examples? You have to invent the factorial itself from inductive reasoning alone. This doesn't seem like a simple problem anymore. Here's an example of a definition of factorial using only zero successor. There's a significant amount of code. In any case, Parallel has managed to do it. Parallel has discovered the following program from scratch without any prior knowledge about addition and multiplication, etc. We only supplied it with successor and zero and 6 examples, aka the value of factorial from 0 to 5. And then Parallel came up with everything needed to compute factorial on its own. We know that the success of Parallel depends on our decomposition of the program into a template colored in black and host colored in red. The template uses recursive to express a quite general class of programs and is iterated in the outer loop. And we then use stochastic synthesis to synthesize non-recursive terms colored in red. More on this later. Parallel has shown excellent ability to come up with programs from very little prior knowledge, which is unprecedented for previous systems. Let's see a few more examples. First, it invented 3 different algorithms for list reversal. It also came up with the Fibonacci sequence, again from only successor and zero without any knowledge about addition. Then, Parallel also came up with different traversal orders for trees, this time from only counts and nil to collect the result. In contrast, Parallel systems Smith require at least append as a library function. Let's look at the 3 list reversal examples closer. The following is one solution to the list reversal problem found by Parallel, which roughly corresponds to the following Haskell program, with the inner loop appending an element to the end of the list, a list accumulator. The following is another solution found by Parallel, which roughly corresponds to the following Haskell program. This time, the solution uses the inner loop to append an element to the end of the resulting list. Finally, the following found by Parallel utilizes continuation passing style to encode top-down traversal. This is enabled by supporting using a function as your accumulator type. This roughly corresponds to the following Haskell program. Judging from the performance of our system, it seems that we must be doing something right. It turns out that its success depends on a few design choices, including the use of parallelism. However, once we figure out the right thing, the algorithm is pretty robust and is able to solve many different problems. I'll now walk through this approach we are using. Our target language is a standard, simply typed functional language. The first ingredient of our synthesis algorithm is a stratification of the language syntax into templates and hosts. A template is an incomplete program with multiple typed holes. For example, the following is a template which gives a correct list append function if all holes are filled in appropriate terms. The power combinator enables primitive recursion, which I will explain later. For the time being, let's note that the template defined the shape of the recursive program and introduces a number of variable bindings, which can be then used inside the hole. While we basically allow arbitrary target language construct to appear in the template, we restrict the syntax of the terms to be filled in holes. In part, holes can only be filled with a first-order subset of the target language, which are just applications and constants. Neither recursion nor variable bindings is allowed to appear in whole terms. This turns out to be crucial because it makes the search space for whole terms much more well-behaved. Essentially, whole terms are just straight-line code, a problem with stochastic synthesis has previously been applied successfully. So a little explained in detail, the template introduced recursion via the paramorphism combinator, which is the second essential ingredient of our algorithm. The third ingredient is to employ stochastic search technique to solve for whole terms. The search procedure itself is embarrassing in parallel, in stark contrast to any previously deduction-based systems. This is made possible by our stratification, which simplifies the syntax for whole terms which we need to search upon. Condition the search space of whole terms to be well-behaved. Our approach shares similarities with program sketching, which allows programmer to specify incomplete prompt for synthesis. Our motivation privately focuses on conditioning the search space of whole terms so that stochastic search becomes effective. We use a fixed set of systematically generated templates. This is a high-level overview of our synthesis algorithm. I will now go into some more detail. First, paramorphism. Paramorphism is an instance of recursion schemes, which are just canned recursion patterns. It has been advocated in the functional programming community because it handles the hard part of writing correct recursion patterns on data types, and the program just needs to write non-recursive logic. Catamorphism, or fold, is a simplest example of recursion scheme. When acting on list, it is just a plain old write fold. The fold combinator accepts a list, an initial state value, and the function that takes a list element, a state value, and then produces a new state value. The fold combinators then iteratively apply the function to the list elements in bottom-up order and returns the final state value. Paramorphism is a generalization of fold, which gives function f access to not only the element at the current list head, but also the list tail. Note that I'm writing everything specialized to list here, but paramorphism, like other recursion schemes, can be extended to arbitrary algebraic data types. A fully general way to write it would require the use of functor fixed points, which I omit here. An example of paramorphism is factorial. In that case, we are dealing with natural numbers rather than list, but it's very similar. A fold over a natural number is just you loop for n times, and the paramorphism gives the loop body access to current iteration count. It is impossible to write factorial as a catamorphism over just natural numbers without using tuple types, but straightforward to write using paramorphisms. In the current power system, we focus on templates in the form of properly nested paramorphisms as a generalization of proper loop nest. It is straightforward to extend the set of templates to include, for example, several sequentially chained proper recursion nests, but a single proper recursion nest is already expressive enough for all of them. As we have seen in previous examples, the paramorphism combinator can have different instantiation when it recurses on different type of structures, say list or natural numbers, and at different state types. This results in some degree of freedom, even if we settle on proper recursion nest as the overall shape of the recursive program. Therefore, we write a fold generator that instantiates a template given the state type and the list of types to recurse on. For example, we get the following template that uses list of natural numbers as a set type and recurses on a list of natural numbers and a tree of natural numbers at recursion depths 1 and 2 respectively. Note that we're recurring on a non-recursive type, such as Boolean, the paramorphism will degenerate into a pattern mesh. We then use an outer loop to enumerate combinations of state types and recursion types and run the inner loop, which is the stochastic synthesis for whole terms on all these templates concurrently. Now let's talk about the inner loop. The goal of the inner loop is to fill in holes in the template to produce a correct program. Note that the whole terms are non-recursive and are essentially straight-line code. We use a guided stochastic search for this task. First, we have a cost function measuring quality of entire programs. At each step of the search, we apply a single step of mutation, to the non-recursive whole terms in our candidate program. Different kind of rewrites include substituting any subterm with a variable and adding or removing one layer of application. We specifically accept the proposed new candidate program based on our cost function. The cost function consists of two terms. One measures the size of the candidate terms, and the other measures the correctness of the candidate terms. The constant alpha sets the weight of the two contributions, and we set it to 1. The correctness term is computed from the added distance between the actual program output or example input versus expected example output. Finally, let's end the presentation by looking at an example of our search algorithm running in action. We'll look at this template generated from our appropriateness generator. It is a single level of paramorphism over list data type. At the beginning of the search, which is point A, each hole is initialized with its default candidate. In this example, every hole has type list of natural numbers and is initialized to nil. This initial function also returns nil, regardless of input. The first significant decrease in the cost function occurs after fewer than 10 accepted proposals when the term in the second hole is rewritten from nil to L2. We now have a function that always returns its second list argument. This function has the lower cost because the second list is more similar to the desired output, which is a concatenation of two lists. The search discovers this function at point B. The next significant better function is found at point C. This program iterates over L1 and adds a constant 0 to the ahead of the result for every iteration. This function has a lower cost because its output is even closer to the desired output, with the correct length but potentially correct element in the final list. Finally, we discover the correct append function at point D when we change 0 to a variable h in scope, which is the element of the first list. In summary, we have developed a new synthesis system which uses stochastic synthesis to fill in holes in paramorphism templates. The system can handle nested recursions thanks to the use of recursion schemes and can synthesize surprisingly involved programs with very little prior knowledge. We use paramorphism templates to reduce the problem to synthesizing non-recursive terms so that stochastic synthesis can be effectively applied. Thanks to the use of stochastic synthesis, the algorithm is also embarrassingly parallel and can make use of today's increasingly massive computation power. Finally, our code is available at the following address. That's the end of my talk. Now, question and comments.
Thank you.
Check. Hi, thanks for the excellent talk. So I have a question about the cost function part. So it seems like in the cost function, there is an added distance, right? So do you require that the output to be structural? For example, the inductively defined natural numbers. So what will happen if the output is just a natural integer, native integer in languages?
Yeah, good question. Let me find this.
Yeah.
Yeah, so it is defined by formally defined by regarding the algebraic data type as a labeled trees and computing the added distance. But for natural numbers is a very good example. So when you represent it as a moving integer, there's an efficient way to compute the distance, which coincide with the formal definition. The result is just the absolute value of the difference of the two natural numbers, right? Because the natural number is when represented in unary, the tree of depth n. The added distance is exactly absolute value n minus m for n and m. Yeah, so the system is extensible, and we formally define the cost function as added distance, but you can supply your own added distance function when you have some like some black box types. That answer your question?
Hi, thanks for your presentation. Seems like really awesome work. I was really curious, did you run an ablation on your, I guess, stochastic synthesizer versus something like a bottom-up with observational equivalence to see how much benefit you get from that approach? It seemed really interesting.
Oh, yeah, exactly. So in the paper, we tried to change the stochastic synthesis with, I think we can let the result take. In fact, the second column is when we change the stochastic synthesis part to using a bottom-up, actually using a best first search, guided by some cost function, but but deterministic and in theory have some better theoretical guarantee like completeness. But when running in action, we see that stochastic synthesis show like significant advantage over that, and we have some motivation of like that's an idea of why happening in our paper, and basically stochastic synthesis it is possible to because if you're using best first search, which is a greedy approach, then which is a greedy approach even guided by cost function, and it will be more difficult to make change to the program that will require at least 2 edits in different places to make the overall cost function reduce. But it has a non-zero probability for the stochastic synthesis variant. Yeah. So in summary, basically, we tried a deterministic approach and compare it with the stochastic synthesis variant, and it seems that stochastic synthesis variant do have some significant advantage. Does that answer your question? Thank you.
Sort of, I think the complementary question to that, which is that when you use a edit distance sort of a cost function, you're kind of assuming that you can get closer to the solution, and that depends on the cost function, naturally leading downhill towards the correct thing, but not that cost function might not always be available. The edit distance, only some problems would have that structure, I would think. Have you run into synthesis problems that you just can't solve because that cost function just doesn't lead you to the solution?
So for the problem that we tried, which are all defined using algebraic data types, the cost function is pretty effective. And I think we also have some motivation for what that is the case, because when we limited, say we ignore library functions for now, and if we limited the whole terms to be just constructor applications, then edit distance exactly measures the distance between 2 execution traces, right? Because the only way you can construct the value is to apply constructor application, and then the difference in the program trace that lead to this value are exactly the edit distance when you regard the output as labeled trees. Yeah, so that's the motivation, that's the intuition, and also in practice it turns out to work pretty well for at least problem defined with algebraic data types. And that's basically what I have to say.
Thank you. Thank you. Thank you for staying up late. Oh, sorry. No one more question. Yeah.
I was wondering if you tried comparing against burst empirically.
Yeah. It's also included in one of our. Oh, actually, we didn't include it in our comparison. We haven't compared it empirically. I think our reason for that was basically when we look at burst, it seems to be working on an imperative language, which is quite different from what we're working on, because everything we work on are purely functional. Yeah, so we haven't did that comparison.
Burst doesn't work on an imperative language; it's a functional language. But anyway, I was just curious. That's all.
Okay. Yeah, we did include it in our related work. Yeah, but we didn't include it in the evaluation.
Thank you. Okay, let's thank our speaker again.
Thank you.
Okay, our final talk, Reward-Guided Synthesis of Intelligent Agents with Control Structures by Guofeng Cui, is also remote. Please keep talking so we can tell when we can hear you.
So I'm talking.
Great. We got you. Please share your slides.
Okay. I'm currently sharing the slides.
Thanks. We'll have them up in a second. Okay, you're ready. We're ready for you to start now. Thank you.
So when I switching slide, can you see the next slide one? The next slide.
No, you're in the correct mode.
Right.
Oh,
so
sorry.
can you, I'm switching between the first and second
everything's
slide.
good.
Okay, so now I'll just get started.
Yes, please start.
Okay. Hello, everyone. I'm Yuning Wang from the Automated Reasoning Group of Rutgers University. Today, I'm going to do a presentation about our paper, Reward-Guided Synthesis of Intelligent Agents with Control Structures. My co-authors are Guofeng, Wenjie, and Professor He Zhu. In this talk, we will present a program synthesis approach for robot learning from reward signals. The synthesized program will serve as controllers for the tasks. For example, in the ant maze environment on the right, the task is to instruct a robot to reach the target region. The program on the left will be used as a policy based on the perception functions. The policy will output an action that will be carried out by the robot in the environment. What this program does is make the robot move forward. If it's obstructed in the front, it will turn right, and if there's a path on its right, it will turn right. Interaction with the environment will receive reward feedback that will be used to synthesize better programs. If you are familiar with deep reinforcement learning, you will recognize that our problem setting is actually similar with DeepRL, where a deep neural network policy is used to interact with the environment, and the environment will provide reward as feedback to train the network. Although DeepRL has demonstrated great performance on some domains, we have observed that DeepRL currently have two issues. First, the generalization problem. The trained neural network from the simple maze cannot be directly used in mazes with more complex layouts. Second, DeepRL lacks interpretability. For our humans, the deep neural network policy looks like a black box, makes us unable to trust or verify it easily. Our work is an instantiation of programmatic RL, whose policies are represented by high-level programs. The benefits of programs are that it can be inspected and understood by humans, so it has better interpretability. Moreover, program policies also have better generalization capabilities due to its inductive nature. Examples of programmatic RL algorithms are either distilling a program from a pre-trained network or training a differentiable program with existing reinforcement learning algorithms. Both of them have their shortcomings. For example, both of them rely on the success of DeepRL for enabling programmatic RL. What would happen if DeepRL algorithm fail in certain environments? Actually, DeepRL is often not very effective in tasks with long horizon and sparse rewards, which is a common setting for robotic tasks. For example, in the ant maze environment on the right, it has a long horizon and needs approximately 1,000 time steps to reach the destination. Moreover, in the pick and place environment on the left, the task is to control the robotic arm to place the block at the goal. This task has sparse rewards because the reward is only given to the agent after completing the whole task. So if we naively use a DeepRL algorithm to solve this one, the agent will never gain any rewards during exploration. As a result, there is no reward signal for the algorithm to learn. In general, DeepRL is not very effective for long horizon and sparse rewards tasks because the number of robot environment interactions needed for exploration grows exponentially with the number of steps required for finding the rewarding signals. Now we introduce our solution, Rigorous, abbreviated for reward-guided synthesis, that directly synthesizes programs from reward signals. The main idea of Rigorous is to compress the agent exploration space using language constructs such as conditioned loops. One such example of compression is that if the robot learns to traverse one room, then such behavior can be encapsulated in a loop to traverse all other rooms, leading to more effective exploration. In our Rigorous framework, the synthesis algorithm takes in 3 inputs. The first input is a robotic environment. The other 2 inputs are user-defined reward functions and domain-specific language. The objective of Rigorous is to generate robot control programs that guide agents within a robotic environment to sequentially take control actions, maximizing the expected reward received from the environment across all possible trajectories she from the all possible initial state S0. The DSL of Rigorous contains the domain-dependent states abstraction H, the control action C. The condition B can either be the state action predicate H or its negation. A statement S can be either the while loop or a if-else branch. It can also be the concatenation of 2 statements or just a control action C. So in our setting, we assume an object-centric view in which we know the 3D pose of each object in the environment. Then these poses are used to define state abstractions in the domain-specific language. For example, in the maze-like environment, the state abstractions may contain present object, which checks if an object is in front of the agent. So we can see that the state abstractions act as perception functions that describe the spatial relationship and physical orientations among the environment objects, including the robot itself. Moreover, robotic tasks are task agnostic, which are can be reused in other tasks. So in Rigorous, we consider the setting of sparse sparse rewards. Rewards are only given to the agent when the agent completes the task or achieves a significant step. For example, in the maze environment, the agent only obtains the reward after reaching the target region. In the pick and place environment, the agent receives the reward after placing the block at the goal region. Rigorous use rich control flow structures to compress the agent exploration space. However, this advantage comes with the trade-off of introducing a large program search space. For example, in the multi-room navigation task, the agents need to traverse several rooms with closed doors to reach the green square goal. On the right, we show the synthesized program for this environment. You can see that it's a large program with 3 while loops and several conditional statements. This means we need to explore a large portion of the program search space before finding the solution. The figure on this slide explains the strategy Rigorous uses to address the large program search space challenge. First, the sketch generator generates high-level loop structures with the loop body yet to be filled by the loop completer. Second, the sketch completer uses on-demand synthesis of conditional statements to further reduce the program search space. Third, the program synthesized for simpler tasks can be added to the DSL as new skills to be reused in the more complex task. We take the clean house task as a running example. The robot aims to navigate the environment to pick up markers placed adjacent to walls. It has 4 state abstractions to check whether the marker is present or it's in front, left, right is clear. It also have 4 actions to navigate the robot in the maze. This task is similar to the ant maze task as we've seen before. The sketch generator will use Monte Carlo tree search over this sketch grammar to guide the sketch search directions. The loop sketch can only derive either sequential or nested loop structures and fill in only the loop conditions. After generating a loop sketch, the statement inside and after the while loop will be yet to be filled. Suppose Rigorous has already explored some sketches on the left of the tree. Now the Rigorous will explore the will not present marker sketch in the blue box. The node score are yet to be determined. Then riggers will send this sketch to the sketch completer. Once the sketch completer gets this sketch, it uses top-down execution-guided program synthesis to fill in the holes in the sketch. The programs are expanded as a tree shown on the left, and partial programs will be evaluated according and ranked by their rewards in the search queue. For each action, the pre and post condition are inferred as logical formulas over state abstraction predicates based on concrete execution states. This will help riggers to synthesize conditional statements on demand. Take this program with a single move action as example. When the move is executed for the first time, we will record its precondition. In this case, the condition is not left is clear, front is clear, and not marker present. After executing several steps, we will meet a new state that doesn't satisfy the presumed precondition because left is not clear. To synchronize this conflict, riggers insert a new if left is clear statement to handle this unseen state. Then riggers continue to fill in the missing holes in the newly inserted if branch. When the program is execution continues, it will meet another unseen state that has not front is clear. Again, this conflicts the existing precondition, so riggers will synthesize another if branch to make the agent turn right for this unseen state. The sketch completer will stop working on this sketch when it uses up all its budget. The best program found for this sketch is shown here. The program will collect exactly 1 marker out of 10, so it will receive some partial reward. The reward signal is then sent back to the sketch generator. So the sketch generator will backpropagate the reward signals derived the path of the derivation of sketch. As a result, the node score on this path will be updated to 0.1 because the program can pick up exactly 1 out of 10 markers in the environment. After updating the node scores, the search direction is steered towards the sketches that use the not marker present as the loop condition. These nodes makes riggers more likely to find the sketch that will eventually solve the task. Then, after some iterations, the generator finds this nested while loop structure sketch and sends it to the completer. By using this new sketch, the completer is able to find the solution program that is for reward. Other than the two-stage synthesis technique, riggers uses the curriculum synthesis technique to further compress the exploration space. This is useful when the robot is assigned a series of related tasks, so the program for simpler tasks can be reused in complex ones. For example, in the multi-room task, the riggers first find a successful program called multi-room get to instruct the agent to reach the goal. Then riggers will leave this program to find a arbitrary object in a room. This skill is named as skill with script J. Then the robot is required to solve a more complex task called locked room. In this environment, the robot needs to first find the key and then unlock the door before it can reach the goal. The DSL of this environment has 2 more extra skills that come from the multi-room task to reach the key and lock the door. Consider this partial program to synthesize the missing hole in the inner if branch. If riggers execute this partial program, the agent will stop in front of the door. Then the riggers can invoke this skill J function to get to the key to open the locked door without having to explore the raw actions. So this demonstrates riggers can how curriculum synthesis greatly compress the exploration space using just a single action. In our experiment, we evaluate riggers on Carol tasks and compare it against 2 baselines. In these tasks, the Carol robot is instructed to traverse the environment and to pick up or place markers at designated locations. The DRL baseline, represented by black curves, is a PPO agent that takes raw environment as input. The PPO algorithm is a state-of-the-art DRL algorithm. The DRL baseline, represented by the black curves, is takes the abstract state predicate as input and outputs the same action as riggers. DRL ABS shares the same input and output as riggers, which makes it a fair baseline. So in our method, rigors represented by the red curve. So the x-axis are the number of environment interactions, and the y-axis are the reward signals. So in our experiment, rigors finds better programs with more efficiently in almost all tasks. We also evaluate the curriculum synthesis part of rigors on a sequence of mini-grid tasks. The agent is tasked to reach the goal region by navigating the complex maze. On the left, you can see how the skills are reused from simpler tasks to more complex tasks. In the diagram, the x-axis are the number of environment interactions, and the y-axis is the number of solved tasks. So rigors is able to solve more tasks with curriculum synthesis than without curriculum synthesis or the DRL ABS baseline. The rigors can also synthesize robot control programs for tasks with continuous stochastic state spaces. We evaluate rigors on long horizon and sparse rewards tasks, such as the highway. So in the highway, the actions of other cars are non-deterministic, and we need to control the ego vehicle to reverse the highway as fast as possible. In the pick and place environment, the block can be slippery and prone to falling from the gripper, which makes it challenging. And in the space environments, the task horizon is as long as 1,000 steps. For those continuous robotic tasks, rigors have better sample efficiency and solve more tasks than baselines. Interested readers, please check out our paper for details. In conclusion, rigors uses rich control flow structures to compress the agent exploration space, and also uses the two-stage program synthesis and curriculum synthesis to handle the large program search space issue. In our experiments, rigors outperforms various DRL and synthesized baselines in long horizon sparse reward tasks. So thank you, everyone. That's all for our talk. I'm open to any questions.
Thank you.
Okay, so I have a question regarding how you deal with the problem of if you add a new skill to the robot control DSA, this effectively changes the amount of actions you can take, if I've understood correctly. How do you deal with this dynamics action space? Because, yeah, if you could elaborate on that, that would be great.
Right, so just for an example, so once we solve this simpler multi-room environment, we get this new skill, and for the next, we add this skill J with when called on other object that the robot can interact. So for example, in this environment, the robot can also interact with the key and lock door. So those two skills are added to the DSL. Then, since we use like a top-down program synthesis to find the program, then those all those possible DSL actions will be considered during this top-down search. And you're right. So as we move to more complex tasks, the number of actions actually increases. So this brings a more burden to the program synthesizer. But on the other hand, the exploration space of the agent in the environment greatly reduces, because now we can think of that we now have higher level actions rather than lower level move or turn right, turn left. So hopefully it's more efficient for exploration, because now with just a single action we can accomplish an enormous amount of interactions with the environment.
If I could have a follow-up question, do you have to predefine what skills the agent is able to learn from the beginning, or is it able to synthesize itself some skills that may be part of a larger problem that you don't define beforehand?
Right, so we only give it a reward function, actually a sparse reward function. For example, on the multi-room environment, the reward is only given when the robot travels all rooms until it's reached the green square goal. So it needs to synthesize the function to traverse each room on its own, which we haven't defined. We only tell it to go to you go to the final location, but the program synthesizer finds the way to interact with the environment to traverse the rooms. And similar for this locked room environment, where we only give it reward when it's reached the green square goal, but it learns to pick up the key and open the locked door on its own by interacting with the environment using the curriculum synthesis and the two-stage program synthesis. So I think yes, it actually finds some behavior that we didn't prescribe.
Thank you very much.
Yeah, thank you.
Okay, so in some deparallel domains, we might want the control programs or control policies to be randomized, which I guess would require some randomness in the program. And sometimes we might want the control policy to be history dependent, which might require the program to have some internal state to be continuously updated. Could you maybe give us your idea on whether your approach could be extended and used in such domains with such requirements?
All right, so let me first explain the state part. So actually, so when you use a program as a policy, it's internally indeed have some memory. So let me show you with such an example. For example, on the skill task, so you can see that there are a lot of the move actions. So at least in the first while loop, there is a move. In the second while loop, there is also a move. In the third while loop, there is still a move. So the robot will do the same actions, but in different situations. So you can understand that initially we will move, and after some thing happens, we do something else. But if we are in a new situation, we can still do the move. So I think this can be regarded as some internal memories of the agent about the current state it's in. So, but I mean that's just a part of the question. So we can still also add more. Right, I think that's memory in some degree. So as for the randomness part, you're right. So some policies need to be randomized, but actually the in the environment we define. For example, in the current environment, there is no randomness for its actions because the move forward is just move forward, turn left is just turn left. However, for the continuous tasks that we are working on, so for example, in the maze, the move actions can be the move or its actions can be pre-trained neural networks. So the low-level action when it's called can be a neural network, which I think it can be extended to a randomized policy from the RL, but this will be encapsulated in the lower level action that the synthesizer doesn't have to know. So that's one way I think.
We're really out of time. We should just take this offline. Thank you very much.
Okay, thank you.
Okay, thanks everybody, and we'll see you again after lunch.
Started. So welcome to the Potpourri 2 session. We have 5 talks for you today. I'm the chairing the session. My name is Caleb Stanford. And the first talk will be on Falcon, a fused approach to path-sensitive sparse data dependency analysis. So please take it away.
Well, hello. It works, right?
Are we good in the back?
Hello. Hello.
Good. We're good.
Okay. So good afternoon, practitioners and researchers. Welcome to my talk. And I'm the third author and also the presenter. I come from the Ant Group. Okay, Ant Group is actually the largest e-payment service provider in Asia. At the company, I lead a team to develop static analysis tools for industry use. And Falcon is one of the most important algorithms underpins our static tool. Okay, now today, I'm happy to share the details of Falcon. First of all, a little history about Falcon. Falcon actually is derived from the CODA project, which is initiated in Hong Kong, UST. The CODA project aims to solve the most challenging issues in static analysis. Namely, the code is continuous evolving, and the code is developed by different teams across the continental, maybe, and the code size, the code base is quite large. All right, and 4 years ago, in the PLDI, we published the first paper to introduce our pinpoint framework, which is a value flow bug detector, and the Falcon is also mentioned in that paper a little. Okay, the Falcon is used to provide the most precise value flow graph for the pinpoint static analysis tool. In the next few years, in the next few years, we built quite a lot of utilities upon Falcon and Pinpoint. And this time, we think, and also Falcon is evolving and adapt to various applications, right? And this time, as we think Falcon is mature enough, and we decide to open it. Okay, back to this paper. Data dependence actually is all about answer the depth use related queries. Okay, for example, in this code snippet, we want to know if the value of A relies on the value of B. All right, that's simple. The question is simple, but answer this question is not simple, right? This is actually a long-standing open problem because the pointers, function calls, and the many other program constructs complicate the data flows. All right, but nevertheless, our goal is still to a moon. All right, and we want to design a highly precise, which means path-sensitive algorithm, which can finish on a commodity regular server. All right, for minutes lines of code. This is our goal. But the obstacle for our goal is the so-called anything path explosion problem. Okay, the problem is actually intuitive. This is because we often, during the program analysis, we often link the path segments, okay, in the Cartesian product manner. All right, for example, here this is a simple assignment, right? Star P equals to Q under the path condition delta. And if we suppose P points to two different objects under the path condition phi1 and phi2, and the Q points to different objects under the conditions phi3 and phi4. Okay, after this assignment, we can create 4 path conditions, and by combining the path condition, all of them. All right, so these path conditions can create high redundancy, both in storage and constraint solving. Okay. In the previous paper, in the pinpoint paper, we almost solved the storage problem of the path conditions. Here, in this paper, we are going to address how to create less path conditions to make the constraint solver easier. Okay, the existing works, of course, not address the problem well, right? The first category of approach is like the symbolic execution. Symbolic execution is for many years struggling with the path constraint solving problem, right? So we do a lot of endeavors, but we still never heard of any report of symbolic execution for many lines of code, right? The second kind of approach is a layer approach. It's a layer approach, and the represented work is like the sparse analysis. And we think sparse analysis is very promising. But the problem here is the existing sparse analysis often use pre-computed point analysis, and which is path insensitive. And most of the time, it is actually flow insensitive, right? To build sparse representation. Okay, but that sparse representation will have a lot of spurious data flows that will cause disaster for the followed-up path-sensitive analysis. Make it slower, make it traverse more edges, and so it's not scalable and efficient. Falcon also follows the idea of the sparse analysis. We process all the functions in the bottom-up manner, okay? And for each function, we perform the on-the-fly sparse analysis and the semi-path-sensitive intra-procedural analysis for each function, okay? And the result is we generate sparse points to sets and a data structure, a specially designed data structure called SEG, okay? It's, this is actually kind of a sparse value flow graph. And in the inter-procedural phase, all right, so we inline the SCG and the sparse points to sets from the caller, from the callee to caller, all right? We at the same time, we instantiate the symbolic objects. The symbolic objects means the memory locations that are unknown when we analyze a function, all right? And after analyze all the functions, and we can collect the formal and actual, collect the SEGs by linking the formal parameters to the actual parameters. And the result is we call the stitched SEGs. And we can just think it, the stitched SEGs is a similar graph to the exploded supergraph in the IFDS framework. The only difference is that we factor out all the side effects as a formal, input and output parameters on the graph. Okay, so the graph seems like the graph becomes side effects free. Okay, so with this stitched SEG, we can answer any kind of data dependence queries. All right, let's look at the details of the first of the intra-procedural analysis. We only give the high-level ideas here, right? The first key idea is on-the-fly sparsity, which means we should build a sparse representation and the points to and the point information together. Okay, we should not separate them. All right, and the idea is also follows. The idea actually follows the SSA program representation, which means a memory location, whatever is a stack variable or a heap variable, is defined at the program point L, can only be used at the program points dominated by L. Okay, that's a key idea. Let me use the example to say how it works. All right, here is a simple program, right? And our algorithm actually is all about applying the store rules, all right, to all the whole code, and we build a sparse data structure after all. All right. So what is the store rule? Let's look at for example, look at the variable m. The variable m is the first address taken U assigned to X. So in the follow-up, right, all the assignments to star X actually changes the value of M, right? So here, actually, it's a depth to M, right? And we create a depth representation here, to record a depth representation here at line 3. And there's another depth to M, right? This kind of depth to M, again, through the star X. But at this time, we'll also propagate this depth to the dominance frontiers of this basic block. Then you can say at this basic block, right, we record the depth to M for this record, right? Okay, so which means the depth to the M value can be changed at L4, which means, and we'll have a storage, we have a record here. So when we want to know the values of M at anywhere in the program, so only 5 minutes, right? Okay, so we have to, it's the same to SS construction, right? We climb up the kilometer tree and we find that we collect the values along with the dominant tree. So those values can be values that can be read from the program location required. All right. So the second approach is kind of same path sensitivity. Okay, the key idea is like as our empirical study, we have 70% of constraints, only 70% of constraints are satisfiable. So we don't need to invoke a fully SMT solver to solve those satisfiable constraints, right? So, and for the rest of for the remaining of the unsatisfiable constraints, 90% of which can be easily solved. Therefore, we propose a linear time solver, okay, to solve the constraints. We don't need to invoke the fully SMT solver, right? And the result shows that actually, in certain cases, we almost solve all the unsatisfied path conditions. It's not the same. It's actually not the same path sensitive. It's almost path sensitive, right? Okay, the interposition analysis. Okay, we omit the details because it's most of the part of interposition is like the summer-based approach, a traditional summer-based approach, right? We inline the side effects of the collie to the color, okay? And the only difference is that during the inlining, we also record Anderson relationship between the symbolic memory objects. Okay, the Anderson relationship is like the symbolic memory objects is a representation for the memory locations accessed by pointers of the formal parameters. All right. Okay, after we creating the data structures, and then we can use content-sensitive searching to answer queries. And the on-demand searching can be performed either in the self-reachability-based graph traversal, or we can use the summer-based approach along with the client applications to compute the data dependency. Okay, here's the example of how we perform the self-reachability-based graph traversal, okay, right? So if we want to answer what x is, okay, so we know x is loading from PRO N, and PRO means loading from the memory location SO1 to N, and this memory location is actually the anything memory location to SO2 to N in the bar function, and we follow the dependency age along to the W, to return to E, and to V, and back to Q. So we can answer the question X depends on Q. Okay, this is it's very similar to IFDS tabulation algorithm. All right, so we give the evaluation result. Falcon and Pinpoint are both built on top of the LVM and these 3 SMT solver. Right, and we support most of the C and C++ features. The machine is like only 40 core CPU and 256 gigabytes memory, right? It's very common. We evaluate by creating the value flow graph, and based on the value flow graph, and we try 2 applications like the scene slicing and user-free bug detection. This is the benchmarking subjects. Okay, from here we select some open source famous open source projects that's very real, and you can say the Firefox is almost 8 million lines of code, right? This is the largest subject with everything in related works actually. Then the comparators are majorly from the SVF. Okay, this is another state-of-the-art value flow-based bug finding tool. All right, and all of the rest are the variants of SVF, and the DSA is coming from the LVM community. And of course, we are more efficient and more scalable, right? So we quickly go through. And the synthesizing is also the same, and we can orders of magnitude faster than the SVF-based approaches. That's only flow sensitive and content sensitive. Okay, it's not path sensitive. Well, we can produce much smaller slices, all right? And for the last experiment, that's a user-free detection. And we can say this also very fast, and especially compared to CSA. CSA is the bug detection tool coming from the Clown project, right? And we configured with these three. And well, because this is a symbolic execution approach, therefore it's 1,000 times slower than us. Okay, so our approach is more practical, and even that, we are faster. We also achieve higher precision. Okay, and we can say there is often an industry requirement of 30% of false positive rate for applying static tools in industry use. Here comes the conclusion, all right? And so our approach is, if you want to design a data dependency analyzer, be on-the-fly sparse, be semi-path sensitive, and be on demand. All right, time for question. Thank you.
All right, thank you for the talk. Do we have any, we have a few minutes for questions. If you want to ask a question, come up to the microphone. So I'll ask a couple of questions. So my first question is about what you do with false positives. So as I understand it, one of the big problems with this type of static analysis is sometimes if you encounter something like a function pointer or another pointer that's very difficult to analyze, it ends up being basically all possible data flows.
Yeah, sure.
So what do you do about these sorts of situations?
Well, okay. So we actually published a lot of paper in UPSLA last year about how to build a precise call graph. Okay, ahead.
Sorry, can you speak into the mic? Or
okay.
Maybe.
Mic, right?
Maybe it was okay.
Okay, sure. I mean, yeah, we build the call graph ahead of the Falcon. That means, and we use the cocktail approach that was published last year in the UPSLA conference. And well, it's after that the call graph is clearly should be carefully handled. All right. So that will otherwise will other things like we will process also create quite a lot of spurious value flows, right? So because of wrong connection between the functions. All right, okay. So but I cannot. I don't think I have time to give details about the core of construction. All right. So if you have time, we can discuss after talk.
Okay. Thanks. I have a second question, which is. So have you thought about the problem of how your static analysis would work on updates to the code? So for example, I have millions of lines of code and your scalability looks very good, but maybe I change one particular function or one particular module. Can I rerun it in an efficient way?
Yes, that's the reason why we use the compositional summer-based approach. We could just reanalyze the code that's changed, right? And to bottom up, to inline the changes into the colors. Okay, that's well minimize the code that we should reanalyze. Okay, that's be compositional. That means.
Okay, thanks a lot. Do we have any other questions from the audience? If not, then I think we can move on to the next speaker. So let's give our speaker another.
Sorry, just not to say is my last job is to give advertisement for my former supervisor. Okay, the Hong Kong UST is recruiting faculty. Okay, and Charles is the person in charge, and he's sitting there. Maybe you guys who is interested can can visit him and talk to him. Don't be hesitant. Okay, right. Thanks a lot.
Okay, thanks. Let's give our speaker another round of applause. All right, so let's bring the next speaker up to get set up. So our next talk is about a proof recipe for linearizability. Sorry, one second. Yeah, so our next talk is about a proof recipe for linearizability in relaxed memory separation logic. So whenever you're ready, please take it away.
Okay, it is clear enough? Okay. Hello, I'm Sono Park. Today I'm going to present my work on a proof recipe for linearizability in relaxed memory separation logic. First of all, what's linearizability? Linearizability is a strong coordinates condition for concurrent data structures. Let's consider a concurrent trace where 3 threads are accessing a concurrent stack at the same time. In this situation, the linearizability of a concurrent stack guarantees that there exists a linearization point within function execution such that the linearized execution satisfies the sequential behavior of the stack. And this simple idea has been captured by the logically atomic triples in separation logic. The key idea of it is that at the linearization point, we make an atomic transition from the resource in the precondition to the resource in the postcondition. And it is well known that these logically atomic triples imply linearizability. However, the problem is that this simple style of specification is not applicable to relaxed memory because it is too strong to describe all the relaxed behaviors. I elaborated about it using the same example as before, but now in relaxed memory consistency. In relaxed memory consistency, each thread may not read the latest value stored on the memory. As a result, the second thread may fail to pop anything from the stack. In this scenario, the linearized execution does not satisfy the sequential behavior of the stack. So to explain this behavior, we have to consider the reordering between events. In particular, if we reorder push 1 and empty pop as shown in the screen, then you can easily see that the linearized execution now satisfies the sequential behavior of the stack. So in summary, the lesson from this one is that in relaxed memory consistency, we have to consider the event reordering. However, this event reordering should not happen too much. Consider this another example where one thread executes push and then pop. In this case, these two events have a very strong causal order between them, so the reordering between them should be forbidden. And by forbidding this reordering, we can now guarantee that the pop operation should succeed in popping out the previously pushed value. So the lesson from this example is that event reordering should not happen too much, and it should observe the causality between events. These two lessons have been already considered by our prior work on a new style of specification called linearizable history specification. The key idea of it is that we maintain the history of all the events that have happened so far. And using the history, the specification guarantees that we can reorder some events in the history to satisfy the sequential behavior of the data structure without violating the causality. And it is well demonstrated that this specification is very strong in the sense that it can be used to verify a large set of clients that uses very complex pattern of synchronization. Now, it is time to focus on the remaining problem, which is that this style of specification is very difficult to prove in reality. There are several data structures that have been proven correct in relaxed memory consistency. And we found that to verify data structures in relaxed memory consistency, we have to spend about 10 times more proof effort. So as a result, some data structures are only verified against weak specifications, and some data structures have not been proven yet. In this situation, our main goal is to reduce the proof effort and increase the scalability of the proof. To achieve this, we first propose a proof recipe for manual verification of the linearizability. And on top of that, we apply proof automation technique to further reduce the proof effort. By combining our two proof recipes, we were able to reduce the proof effort by about 81% compared to the prior work. Consequently, we were able to verify more data structures against strong specifications. And we were able to verify methods fully library for the first time in relaxed memory consistency. If you consider our work in perspective of proof automation, then it turned out that our work is a first work on the proof automation of the linearizability that supports relaxed memory consistency. So to achieve our goals, there were 3 major challenges in proof structure and compositional verification and proof automation. And due to the time limit, we are going to only focus on the first 2 challenges. For the first challenge, I will explain it, to explain our new proof structure. Let's gain some insights from simple invariants in a simple setting called sequential consistency. We will do it using a simple example called traverse stack, which is a very well-known concurrent stack that is implemented as a linked list structure. The invariant of traverse stack is very simple. As shown in the screen, it basically maintains a very strong and intuitive connection between physical state and logical state. And here, you should notice that you should remember that this simple, strong connection between the 2 states plays a key role in easy invariance and easy reasoning principle. We will see why it is so effective by going through a concrete, high-level verification of traverse stack. Let's consider the push operation, where we first read from the head pointer, and then we allocate a new node containing the value, and then we set the next pointer of it. Finally, we update the head pointer using atomic instructions like compare and swap. In this case, at the last step of the operation, we update the physical state. And as soon as we update the physical state, we should also update the logical state following our simple invariant. And here, the update of the logical state can be done very easily because thanks to our simple connection between physical state and logical state. The same story holds for successful pop operation like this. One interesting case is the empty pop case, where we try to pop from the empty stack. In this case, the empty pop case is considered as a read-only event because it does not change the physical state. And thanks to our strong connection between physical state and logical state, we don't need to update the logical state in this case. And in other words, this means that in sequential consistency case, in sequential consistency memory, we have the proof obligation to verify empty pop case is very easy to consider the same example, but now in relaxed memory consistency. The high-level proof structure is the same. We are going to construct some kind of connection between physical state and logical state as we did before. However, the physical state is a little bit complex when comparing to the sequential consistency case because we have to remember the history of all writes to the memory in this case. The logical state is also complex because we have to remember the linearization order of all the events that have happened so far. In this setting, we are going to go through the high-level verification step of the traverse stack as we did before, and while doing this, we are going to find out what's the problem in relaxed memory consistency. The push operation proceeds as the same as before, and the verification of push operation is the same as before. At the last step, we update the physical state, and then we update the logical state at the same time. The same story holds for successful pop operation. However, the main complication comes from the read-only event. In this case, we should consider the empty pop case. To see why empty pop case is the main complication, let's see that the read-only since empty pop is read-only, we do not update the physical state. However, when in contrast to the sequential consistency case, we should now update the logical state in this case because this new empty pop event should be inserted within the linearization order. This means that read-only events can be inserted without changing the physical state. In other words, read-only events have only the weak connection to the physical state. And this weak connection is a main enemy in proof simplification because this means that for a given physical state, there can be a lot of valid logical state that contains lots of read-only events. So this is the main problem that we want to solve for the first challenge. To solve this problem, our main idea is that it is okay to focus only on the right events when establishing our invariant. This main idea has been we encoded this main idea into our new proof structure called object modification order, or in short, we call it OMO structure. the OMO structure basically maintains the total order of only the write events. And the read-all events are just placed below the corresponding write event. And using this object modification order, it is now possible to set up a strong connection between physical state and logical state by only considering the write events. So in short, so as a result, the simple invariants are now possible by only considering the write events. Furthermore, since OMO structure is a specialized structure for dealing with read-all events, we designed several proof rules that is very easy, and these proof rules contributed to reduction of the proof effort a lot. So far, we have discussed our new proof structure called OMO structure that enables simple invariants and easy proof rules by focusing only on the write events. Now, we are going to apply this new proof technique to a more complex situation where we are going to verify a complex data structures in a compositional way. When discussing about to discuss about compositional verification, we are going to use elimination stack as a running example. Elimination stack is another implementation of a concurrent stack, and it uses traverse stack and exchanger as low-level modules. Each operations first make a function call to the corresponding operations on the traverse stack, and if it fails due to the race condition, then it now uses exchanger as a side channel to atomically exchange the two operations between push and pop. And using this example, I'm going to present how we can verify this elimination stack in a compositional manner. In other words, we are going to construct the OMO structure of elimination stack by only looking at OMO structures of lower-level objects. To simplify the proof effort, in this compositional verification, the key idea is that we exploit structural similarity between upper-level OMO and lower-level OMO. And let's see the structural similarity by going through a concrete example. To see the structural similarity, we are going to connect every upper-level event to the corresponding lower-level event using our new relation called the committed relation. Committed relation basically connects the two events whose linearization point coincide. In this example, suppose the push operation of the elimination stack has just been finished by only executing the push operation on the traverse stack. In this case, the linearization point of the upper level push event comes from the linearization point on the lower level traverse stack event. So we connect them using our new relation of committed relation. We can we can continue to establish this relation, and up to this point, we can see that this relation usually satisfies monotonicity. And this monotonicity is very important because it allows us a new viewpoint that the lower level OMO can be viewed as a projection of upper level OMO. This is the structural similarity that I want to exploit. And this is very effective in proof simplification because it allows us to project very complex proof obligations on the upper level OMO to the corresponding and very simpler ones on the lower level OMO. I'm going to elaborate about it with another concrete example. Consider the case where we are going to insert a new empty pop event. In this case, we have to prove the validity of the reordering regarding this empty pop event. And to do this, we can exploit the monotonicity. First, we consider the proving the validity of the reordering with push 1 and push 3, which are connected to the traverse stack event. In this case, we can directly use the monotonicity to project the proof obligation on the upper level to the corresponding ones on the lower level. And you can see that the validity of the reordering on the lower level is already guaranteed by the specification on the lower level object. So we can immediately finish this proof obligation. So all we need to do is proving the other part of the proof obligation. And for that part, we can do a very different kind of reasoning. But due to the time limit, I'll just skip it. And if you're interested, then you can find more details in our artifact. So to conclude, we propose a proof recipe to reduce the proof effort and increase the scalability of the proof when proving the linearizability in linked memory consistency. our method was able to reduce the proof effort by about 81%. And in our paper and artifact, there are more interesting discussions about concrete resources, proof rules, modification of the style of the specification, and also the proof automation idea that uses diaphragm. All our work has been formalized on the IRC 11 separation logic on Coq. So if you're interested, please visit our GitHub repository to see more information. Thank you so much, and I'm now happy to answer your questions.
Okay, thank you. If you have a question, come up to the microphone. I'll ask one or two questions in the meantime. So my first question is about this OMO data structure that you use. So you essentially have the writes ordered in this in this sequential way, and then the reads ordered as attached to a particular write, right?
Yes.
So can I generally think of that as sort of a partial order, or have you thought about using partial orders to model the history instead of sort of sequential relations?
Actually, it is not a partial order because as this arrow is shown as a one directional, in reality we can do it in a bidirectional way. In other words, you can construct the total order from this structure. This exploits the somewhat very complex, interesting property that you can believe that this structure is a two-dimensional high-level structure that maintains the linearization order. So it basically makes a total order in this way. But in a high-level structure, we basically only consider this total order. This is the key point. And this is not a partial order structure. Yeah, I should mention it.
Okay, I guess what I'm saying is, like, for example, you could think of the empty pops as only depending on the init. They don't really depend on each other.
Yeah. In reality, they may have some dependency, but yeah, actually, read-all events have very less effect on the global memory. So we can do this kind of structural optimization, like I say, yeah.
Okay, I'll have to take that. I'll take that one offline. I'll ask one other question then. So you mentioned the results you had in verifying a number of concurrent data structures looked very impressive.
Yes.
I was wondering if you foresee any challenges to extending those proof verification efforts to other data structures. Is it sort of like, are there challenges to the reusability of the proof infrastructure that you've developed?
Okay, that's a good question. And actually, already in our paper, we tried to verify a very large set of concurrent data structures, and also as a follow-up work, we are currently going through a verification of more complex data structures, like very complex hash maps or something like that. And currently, we are seeing that this can be easily adopted in highly complex data structures because it is very general to the concept of the linearizability in elect memory consistency. So yeah, in conclusion, yeah, I think it can be easily adopted to other kind of verification.
Okay, very nice. Okay, so if there are no other questions, let's give our speaker another round of applause. All right, so our third speaker of the session is going to talk about compositional semantics for shared variable concurrency. I think we'll give them a minute to set this one up because we're figuring out which laptop will work for it. So bear with us here if it doesn't work right away.
Yeah. Oh, great.
Yes, all good. Yeah, just clip it to waste panels.
Okay. It's displaying there.
You should go back and go to the slideshow button. Probably.
No, you can share between speaker notes and the actual screen, or not. You can. Hello, everyone. I'm Mikhail Svetlovsky, and I'm glad to be here. And today I will talk about the paper that we did together with Orel Ahaf and Shai Mertenstein. We revised the problem of defining semantics for a concurrent programming language. The motivation is to understand a piece of code, and use such code denotation to justify local compile transformation, that is source common transforms to target, when it can mimic every execution of target from starting state to final states inside every context. We want the semantics to be compositional, that is a command semantics is determined by the semantics of its subcommands. Adequate if the semantic of source is the superset of the semantics of target, when it implies source transforms to target, and ideally fully abstract source transforms to target only if their semantics relate. We work in the scope of shared memory concurrency, which is much more challenging than sequential programs. In sequential programs, we probably know, the denotation is simply a relation between initial states and final states, but for concurrency it doesn't work. For example, in sequential programs, the programs x is 1 when x increments and x is 2 are the same, as both take an initial state and change it with x becomes 2. But only one direction works in concurrent programs, since a parallel context can interfere and observe the value of x in the middle. This problem was resolved already by Brooks in '96. In the semantics of Brooks, the denotation of a comment is the set of all possible sequences of memory-to-memory transitions interrupted by arbitrary environment changes. For example, among the traces of x is 4 when y is 5, we have the following trace. We start with a 0 state, when we write to x, when the environment changes the state to 1 to 3, and when we write 5 to y. This idea leads to a semantics that is compositional, adequate, fully abstract, and has been considered as a solution to our problem. However, we notice that the full abstraction proof only works if the underlying programming language has a special await instruction, which atomically checks for a condition on the state and then performs multiple writes, like this. Such instruction, which can atomically update multiple variables, does not exist in programming languages or multi-core hardware. So we investigated how to develop a denotational semantics for a language without await. First, let us look at an example showing that without await, Brooks semantics is no longer fully abstract. Consider this comment C, write 1 to x and y, then check if exactly one of them has the value 2, and then check if both have the value 2. Comment D is similar, but without the middle check. The transformation from C to D does not hold with await. To see this, we have a context on the slide. Accordingly, Brooks semantics shows the difference. For example, this trace is in the difference of denotations. However, if we consider a setting without await, let's think. Every instruction changes at most one variable. So before reaching the states where x and y equal 2, we should reach a state where exactly one of them equals 2. That explains why the transformation without await is valid. So our goal is to find a semantics that works for a language without await. Our contribution is a new denotational semantics. It is compositional, adequate, and partially fully abstract. We prove full abstraction in two cases. For a language that uses snapshot, which is like an await reduced to only checking, and for a language without snapshot, when the analyzed comments are loop-free. And all our proofs are mechanized in COG. Let's see how we do it. Our semantics still uses sets of traces as denotations, but our traces are different from Brooks. Our traces track every environment step, and the reads are not recorded. Here on the slide, you see an example trace, which consists of initial state, a map from variables to values, an initial store, a similar map for local variables, and then a sequence of actions. Actions are either component writes or environment writes. We define our semantics in two levels, namely concrete and abstract, and here you see a comparison table. The concrete semantic is defined inductively, and then we take a closure of it by some rewrite rules. Both versions are compositional and adequate, and only abstract one pretends to be fully abstract. Let's start with the denotations in the concrete semantics to show. Not that fast. We take a look on how concrete denotations are defined for some simple comments. For example, on the very right from me, we have a case of a store instruction, which says for the comment x is e, where e stands for a local for an expression that uses only local variables. We start with arbitrary state and store. When the environment does some steps along e1, when we write fat of e calculated to x, and when environment does some steps along e2. And on the left, you see this instance for x is 1. Another example for x increments, it goes like this. The environment does some steps along e1 when we read the value of x, which is not recorded. When environment does some steps along e2, when we write that incremented value to x from the point just after e1, and when environment goes along e3. So the semantics of X increments consists of all traces of this kind. We also define the semantics for inductive cases. First, for sequential composition of two comments, C1 and C2, we take the sets of all traces that are obtained by concatenating a trace of C1 with a trace of C2. And we only allow concatenating traces that have the same store and a shared state between them. For parallel composition, we define we synchronize the traces of C1 and C2 action by action. If the left thread writes what the right thread would expect, or vice versa, then they compose to a component write. If both expect the same, then they compose to an environment write. In the other cases, it is not defined, and the example below just illustrates these cases. Okay, let's move on. So far, we have defined briefly a compositional semantics. It is also adequate, and the key lemma to prove this is that a comment executes from a starting state to final state if and only if a trace with corresponding component chronicle is in our denotation. This semantics already supports a wide variety of transformations. We have some structural transformations. We can reorder, introduce, eliminate local operations, and we can introduce and eliminate redundant reads. However, we have not reached full abstraction because we do not support transformations that modify the sequence of writes, as in our increment example. Next, I turn towards abstract semantics, all right, which closes concrete denotations under some rewrite rules. We will denote the closure of a denotation with double square brackets and define the closure using rewrite rules. This circled arrow denotes a rewrite step. The rewrite rules aim to make more transformations provable. Let's revisit our increment example. So this trace has a single component write, and it is in the notation of X is 2, but not in the denotation of the other comment, because they should have two component writes. However, it will be included in the closure. Choosing rewrite rules is our major challenge, because too many rewrite rules would validate too many transformations and fail adequacy, and too few would not validate enough transformation and fail full abstraction. I'm going to present our rules first and then explain how we found them. First rule, called coalesce, says when we have a block of component writes that has a total effect of one write present inside this block, we can compress it. As we can see in the slide, this M1 when write v to x, and when M2 compresses to single write v to x. Condition 1 requires that these are component chronicles, full of component writes, and condition 2 ensures that this effect of a block is like a single write. It is easy to see that this rule covers our increment example. It's good. And another example we can do by this rule is we read from y in some local variable. When we write 1 to y, when we write 1 to x, and when we set back the previous value of y, and it can be seen just as x is 1. And we can prove this transformation using the coalesce rule. Okay. A more complex rule is environment coalesce, which is similar but applies around an environment pivot write. And to compress like this, it is also required that that the variable x has not changed just before that pivot write. This is condition 3 in the slide. And it is needed because of read modify write operators, which can absorb the value just before they write. Let's consider one example. Sorry, I don't have time to explain it fully. Let's get the feeling. So in operational reasoning, to see why this transformation is valid, note that only if we have an environment write 2 to x, just between ifs, when the effect of a comment, either C or D here, is skip, as the value of y would be set back. Otherwise, the overall effect is y becomes free. For reasoning with traces, we compare the annotations and the sequence write free to y when environment write 2 to x, when write the value of y back. We can compress by the environment coalesce rule into an environment write 2 to x. In general case, this trace can also have more environment, but that's not important. And note that if we have a weight, as in Brooks, we can check also the value of y before that environment write. So the transformation fails. We have 2 more rules that allow us to introduce or remove redundant writes. For example, this one validates let A is x in x is A when C to let A is x in C, as well as always a run which doesn't change the value of x before after the read. The second rule allows to introduce a redundant write, and for example, we can use it to introduce a fetch and add instruction which adds 0 to a value, so it doesn't change it. Next, let me overview our compositionality proof. The most interesting part of it is the inductive step in parallel case. For this, we have to prove that adding a parallel thread C2 does not save the subset relation between the notations of C1 and C1 prime. If the trace of C1 prime was rewritten, as you see in green, it probably cannot synchronize with the same trace of C2. So to solve this, we will look for another trace of C2, see this in orange. And for that, we come up with some invariance of concrete semantics. Therefore, if a rewrite rule is admissible inside this kind of arguments, its dual rule should be an invariant of concrete semantics. And this is a guide for us to how to find the rewrite rules. A closer short look on dual rules. The condition that is required from compositionality can be simplified to duality principle. Dual trace here means to replace every action with its opposite, and T1 transforms to T2 by our rewrite rules if and only if the dual of T2 transforms by some invariant into the dual of T1. Here we can observe coalesce rule and its dual disperse. And disperse is an invariant of concrete semantics. Okay, so I skip adequacy proof as it follows simply from compositionality. And a bit of our full abstraction argument. So we want to justify an example transformation. We have a trace that lies in the difference between the notations. And we construct a context just to mimic this trace by taking snapshots and doing every environment right that we're supposed to do in parallel by read modify write operation. It is natural that we have, with this context, we have an execution for target comment as it mimics that trace. But for if we have such an execution for source comment, this would be a contradiction by some analysis on the rewrite rules and constructed context. We also note for loop-free comments case, we can replace snapshots with sufficiently many repeated reads of every variable involved. Let me summarize. We presented a new denotational semantics. It is compositional, adequate, partially fully abstract. In our paper, you can find also read modify write constructs, non-deterministic assignments and loops that we have in syntax, and example showing that without snapshots but with loops it doesn't work, and local version over the rewrite. There are some questions for future work. We still want to know about full abstract semantic without snapshot. We would like to develop a similar semantic for termination sensitive executions in fair runs. And we can turn our attention to weak memory models and higher order language. Thank you. Sorry for
We have time for maybe one quick question. I'll ask a quick question maybe while the next speaker is getting set up, if that's okay. Do we have our next speaker? Yes. You mentioned in the paper that all of your results are fully formalized in Coq.
Yeah.
Did you discover any bugs in the semantics that you had while you were doing the formalization?
What do you mean by semantics that we had?
Did you discover any bugs in your results while you were doing the formalization?
No, it went okay.
It's a quick answer.
Okay.
All right, let's take a
if you want a bit more, I can add that we found some other results, so you can reuse our artifact and prove some more details and change a bit details and see if it works in Coq. When you can prove it. That's it.
Okay, let's give our speaker another round of applause. Okay, so we're on to the fourth speaker of the session, and this speaker will be talking about input relational verification of deep neural networks. So whenever you're ready. Oh.
So hi everyone, I am Devanshu. I am a second year PhD student at UIUC, and I will be presenting our work on relational verification for deep neural networks. This is a joint work done with Chang Ming and Professor Gagandeep Singh. So before going into details of relational verification, I will be briefly introducing what neural network or DNN verifications are. So I guess we are celebrating now. So as we know that neural networks achieve state-of-the-art performance in a lot of different tasks, including image classifications. However, they are not without flaws. For example, it is possible to add small adversarial perturbation to the inputs so that the neural networks misclassifies the perturbed inputs. As you can see in the slides, the perturbed image of the panda gets misclassified as gibbon. The same thing happens with the stop sign as well, which gets misclassified as the speed limit sign. This can be problematic when we consider we are actually using neural networks in safety critical systems like autonomous driving. So we need a way to evaluate the safety of the neural networks. So what to do in this case? One option is easy, is we can just test the neural networks against the perturbed inputs. However, this method has two major drawbacks. First, we can only test with finitely many inputs, and it actually doesn't give any guarantees about the safety of the neural networks. This is where verification comes into picture. So in this case, we formally proved that for all inputs satisfying the input specification phi, the corresponding output satisfies the output specification psi. So this helps us generalize to infinitely many inputs and also provide formal guarantees about the safety of the neural network. Now, however, most of the existing neural network verifiers works with properties that are defined with single executions and are imprecise for relational properties that are defined over multiple executions on related inputs. So this will be the main thing we will be focusing in this talk. So before going into details of relational verification, we'll be introducing couple of relational properties that help us encode a desirable neural network verifiers. The first one we'll be discussing is the robustness against universal adversarial perturbations, or UAPs. So UAPs are input agnostic perturbations. That means we apply the same adversarial perturbation to all the inputs. Actually, most of the practical attacks that are implemented in real life are actually UAPs. This is because UAPs are easy to implement. We can just tamper with the input device, such as attaching a sticker to the lens of the camera as shown in the slide, to implement UAPs. Now, in this case, what we want to verify, like given a set of inputs I1 to Ik, we want to compute the minimum number of inputs that will remain correctly classified for all adversarial perturbation V within the threshold. Now, given we are applying the same adversarial perturbation to all the inputs, the perturbed inputs are actually related to one another. The second relational property we will be considering is local monotonicity. Before formally defining it, we will see why it is important to verify the monotonicity of the neural network. Suppose we are using neural network to predict housing prices. So in this case, we expect the neural network should predict higher prices for a larger house with more number of rooms, provided all other features remain the same. So this can be exactly encoded as local monotonicity property. So in local monotonicity property, we have a pair of related inputs, say I1 and I2, sampled from a local input region around a given input I0. So in this case, what we want to prove that if I1 is greater than equal to I2, then the corresponding output n of I1 is greater than equal to I2, n of I2. Now, as we can see, the pair of inputs I1 and I2 are no longer independent. They are actually related by this linear constants, which we call as the cross-executional constant. So what are the main challenges for relational verification? First one is, of course, scalability. We know that even for ReLU networks, the non-relational verification or individual verification is NP-hard. So for scalability, we want our relational verifier to sound, but we compromise on completeness to ensure scalability. But and as discussed before, the main point of distinction between non-relational properties and relational properties are these cross-executional dependencies. So it is important to exploit these cross-executional dependencies is to improve the precision of the relational verifier. Now we'll be going over the details of the relational verification algorithm with this illustrative example, where we consider these 3-layer networks with 2 affine layers and 1 activation layer with a ReLU activation. We consider a pair of inputs I1 and I2, which comes from 2 different classes. However, we apply the same perturbation V to both of the inputs. Now, what we want to prove in this case, we want to show that for any bounded perturbation V within this threshold, at least one of these executions remain correctly classified. Now, for this example, we construct a product network with 2 copies of the neural network, one for each execution, and we ensure that the same adversarial perturbation is applied to both the inputs, and also ensure the output specification is defined over the output of both the executions. Now, before coming to our algorithm, we will be briefly reviewing 2 of the existing works. First one was published in PLDI' 2023. So in this work, the author do not track any cross-executional dependencies, and they reduce the problem to individual verification. And as expected, given they are not tracking any cross-executional dependencies, this method loses out on precision. In the second paper, which was published in ICLR 2023, the authors take 2 steps. In the first step, they apply individual verifier to obtain a local linear approximation of the neural network independently without taking any dependencies. Then in the second step, they add a additional constraint that actually relates the inputs of the 2 executions. And finally, they invoke a MILP solver to solve this MILP optimization problem. However, the main issue in this method is while computing these linear approximations, we do not track any, they do not track any cross-executional dependencies, and loses us on this precision. So what is the major challenge here? So in this case, we want to track cross-executional dependencies not only at the input layer, but at the subsequent layers as well. Now, the question is how to do that. So in this case, what we observe that the cross-executional constraints from popular relational properties actually share a common pattern. If you look at the slides, that we can see that the difference between any pair of inputs is bounded, and we exploit this fact and track the difference between the outputs of coming from different execution at all layers. And this helps us capture the cross-executional dependency not only at the input layer, but at the subsequent layers as well. So in other words, what we want to do, given 2 copies of the same variable from the product network, we want to compute the bounds on their difference. Now the issue is exactly computing these bounds can be expensive and can, in the worst case, can take exponential time. Now how to resolve this issue? Instead of computing this exact bounds, we compute an over approximation of these bounds, and we use abstract interpretation for this. And for this purpose, we design a new abstract domain called deep poly, which we'll be discussing in the next slide. Now this the new abstract domain deep poly. For each pair of inputs, first track the concrete and symbolic bounds on the individual variables, and additionally tracks the concrete and symbolic bounds over their differences. These concrete and symbolic bounds over the differences actually help us exploit the fact that the difference between the pair of inputs is bounded. Now this concrete and symbolic bounds over the differences are not found in any of the existing abstract domain that are used for neural network verification, and is very specific to deep poly abstract domain. And we also design custom transformers for difference of activation functions like ReLU x minus ReLU y, and we also have transformers for other activation functions like sigmoid, tanh, etc. Now with the deep poly, we no longer need exponential time. We can compute the bounds of differences of all pairs of variables in just order n cube time, where n is the number of nodes in the neural network. Yeah. So with the bounds on the differences, we compute additional linear constants over the outputs of different executions that actually encode these cross executional dependencies. Now, as you can see in the slide, the convex region that are computed with these additional difference constants are actually more precise than the convex region that was obtained in the baseline method. So this is essential for improving the precision of the relational verification. So next, we'll be going over the overview of our relational verifier, which builds on top of the proposed deep poly domain. So given a relational property is defined over k different execution, we first run existing abstract interpretation based verifiers on individual execution independently. This helps us compute the individual bounds on the individual variable and infer constant over individual execution. Then for each pair of execution, we run the deep poly analysis to compute the bounds on their difference and infer the difference constants. Then we collect the difference constants for each of the k choose 2 pairs of execution, and finally we add a MILP encoding of the output specification psi to formulate an MILP problem. Note that this MILP formulation is more precise than that obtained by the baseline, because this difference constraints actually allows us to encode the cross executional dependencies between each pair of execution. Now if you look at the then we invoke a existing MILP solver like Gurobi to solve this optimization problem. Now if you look at the example we discussed, illustrative example we discussed before, actually Raven was the only relational verifier that was actually able to prove it, while both the baselines failed in that case. Now we evaluate Raven with both the baseline with a standard benchmarks. For MNIST handwritten datasets, we see that Raven significantly outperforms both the verifiers in terms of precision. We observe the same result for CIFAR-10 dataset as well. Now for monotonicity, Raven is actually the first relational verifier that actually proves this property for neural networks. However, there exists some other works that uses the bounds on the derivative of the neural network to prove this property. However, as we can see in the slides, Raven is significantly more precise compared to all the baselines. Now we evaluate the scalability of our method with large neural networks that can have millions of parameters. Although Raven is slower than both the baseline, we observe that the main computational bottleneck actually comes from the MILP solver, as you can see, and we are actually able to resolve this issue in one of our follow-up works. So this work, which is going to appear at this year's ICML, what we did, we replaced the slow MILP solver with a custom gradient-based solver that is more scalable. And with this method, we are actually gained a speed up to 60x with a very minute reduction in precision. So we also have another work that is that is under review, which further improves the precision of the relational verifier. Now we also designed a training method that allows us to train verifiably robust neural networks against universal adversarial perturbation. This is actually the first training method that is capable of exploiting this cross-executional dependencies. Finally, I will conclude my talk with 3 representative slides from the presentation. In the first slide, we defined what relational properties in and why verifying them is important for neural networks. Then we introduced deep poly, and with deep poly we computed the difference bounds to infer the difference constant that was helping us to encode the cross-execution dependencies. Finally, we described the overview of our relational verifier. And the code and the full paper are available in the following links. And now I will be open for questions.
Thank you for the talk. Do we have questions from the audience? So I have a question. So in your talk, you focused on 2 relational properties, the UAP robustness and the monotonicity. And it seems like it would be very interesting to look at whether what other properties your approach could be applied to, such as, for example, confidentiality of some inputs, like if the output doesn't depend on some inputs. So have you looked at that sort of thing?
Actually, we looked at a couple of other relational properties in the paper. We skipped that for the presentation. So another property that can be verified with is fairness. So suppose we want to prove that your neural network's output doesn't depend on some sensitive features like race, or so that can be exactly encoded in our framework, and we can verify it.
Very nice, thank you. We have a question from the audience.
Yeah. So great talk, by the way. I had a question that while perturbating the inputs, there might be possibilities where there is problems like exploding gradient. How do you compute lower bound and upper bound in those cases?
Sorry, I didn't hear the last part.
Can you speak into the microphone a bit more?
How do you compute upper bound and lower bound in the cases where the gradients might be exploding or vanishing after perturbations?
So what we did, like you are talking about the existing works for monotonicity, which they compute an over approximation of the gradients using abstract interpretation. So like in that case also you can actually compute an over approximation, right? So it may not be like precise, but it gives a approximation of the gradients.
All right, thank you.
Do we have other questions from the audience? If not, I think we'll end here. Thank our speaker again. Okay, so I think we have one more talk in the session. And our last talk will be on automated verification of fundamental algebraic laws. So whenever you're ready, please get started.
Yep. All right. Welcome to the very last talk of PLDI. Thank you for being here. This is my talk. So this is a joint work with Guido, my advisor sitting right here in the front, and Pascal, who should be looking at me through the camera over there. So let me tell you a little bit about what these fundamental algebraic laws are. But it's not me who will tell you what they are. It's instead Guy Steely who will tell you. So in 2010, so that's 14 years ago, he did this keynote at Strange Loop, and he was telling, well, his advice about how to think about parallel programming. And he ends his talk by saying, everything else doesn't really work. You should just think in terms of algebraic properties at the end. But that was just 14 years ago. By then, we learned that even more properties are crucial for verifying systems, checking these things, distributive, absorption, blah, blah, blah. And these things actually happen more than in just parallel programming. So compilers use them, abstract models use them, in concurrency. So CRDT is being quite hot, essentially being a semi-lattice, which require these algebraic properties. In implementations and in academic work of stream processing, of course, type classes, and in standard libraries. So, for example, in Scala or in D, I guess, whenever you want to fold over a list, they tell you, well, in parallel, they tell you, please make sure the function you give me is associative. But they never actually check that because they really can't. I should say, if any of your work, also your work, people watching me in the stream, if any of you use these things, please let me know, and I'll happily put your paper in my slides. Free advertisement. All right, so now hopefully you've convinced that these things are useful, they're everywhere. And we want to automatically verify them. Because, well, we can hand wave our way, these things are good, but no one really believes us. We can handwrite a proof, so that's if we kind of write a simple paper, but you might pull this face. But worst of all, if you mechanize your proof, then it's quite annoying and tedious. But reviewers like that stuff. They don't like this stuff. So ideally, you would just automatically verify these things. This way, you and the reviewer of your paper are happy. So let me show you how our tool kind of automatically verifies some of these properties. I'll just take a very simple example, just for the sake of these slides, and it's this screenshot from Piano's paper from 1908. This plus that you see all the way down, this is abusive notation, or operator overloading, as we call it in programming. The plus on the left-hand side is addition, and the plus on the right-hand side is the successor function. So we will convert this into code. We choose Scala because this is the language we target. So we create an enum with our case classes, and then we convert the code into, well, the math into code. We get this. But of course, we want to do algebraic properties, so we have to say which algebraic properties apply there, and we add them to the types. So we say addition is a recursive function that has properties of commutative, associative, takes two numbers into another number. And that's the definition. But what do we want to do with it? We want to kind of create a proof tree. So we're all kind of familiar with proof trees, so this is what they look like. But in parts, these are the parts we're interested in. So in yellow is the usual typing context. The goal is the blue. The set of equalities or lemmas or the psi theorems that we know are in green. And we also track disequalities, so things that we know are not true. I'll come back to this later because this turned out to be an interesting insight that we have in our tool. And the problem right now is, how do we find these trees automatically all by ourselves? Our tool follows this kind of very simple but kind of powerful cycle, which is, first of all, it looks at case analysis to generate equalities and disequalities. So which paths we take, which paths we don't take. We then apply some kind of rewrites. So the stuff that we know, maybe that some other function is commutative, we can apply that. Oh no. Okay. Then we kind of, after exploring some of these rewrites, we select some interesting ones. More on this later. And then we kind of do some kind of symbolic execution, and we restart until hopefully we've proven what we wanted to prove, or we get stuck somewhere, or we prove that we cannot prove. Well, we show that we cannot prove, we don't, yeah. But overall, this whole kind of cycle of the main proof is not just by itself, because rarely do we ever prove things without knowing other stuff. So in the global picture of things, there is these things called lemma, which we have to explore, well, generate them somehow. But we also have to prove that they hold true before we actually move on into the proof that we want to prove. So the general structure of the presentation is I show you the big picture, just like the previous slide, then I will go down a little bit more into details until hopefully the time runs out and then there's questions. So lemmas, let me show you the two lemmas that we well, the two shapes of lemmas that we found most interesting to generate. First of all, distributivity. We found distributivity to be quite important because it allows us to just reorder things, right? I want to reason about G before I want to reason about F, or the other way around. And this is what distributivity gives us. But of course, we have to know what these F and Gs are inside the code. As an example, let's take the multiplication that uses addition. So these are over piano numbers, typical stuff. We will not, for example, conjecture that multiplication distributes over list concatenation, because they have nothing in common. Instead, we will just try to look at definitions that use each other. And this will hopefully give us some idea about where distributivity could be used and where the proof of distributivity could be easy to generate. So in this case, we find that multiplication and addition use each other, so we conjecture some distributivity laws, and then we prove some of them, and the ones that pass, in this case the first two, we put them in our context, the other ones we discard them. The other kind of lemma exploration we do is called generalization. Don't read the code, there's a lot of stuff. I will zoom in on the interesting things in a bit. The idea there is I want to take my function, I apply it to all possible unfoldings of the constructor up to one level, 2 levels, however many you want, we just do one. And then you try to relate the output, the symbolic output, to the inputs. As an example, I will focus on one of them, this concat nil and nil being nil, concat being list concatenation. And there we see that there is some kind of a relationship between the input and the output. There's 3 kinds of relationship, or 3 questions we can ask. In red, I'm asking, is concatenation giving me nil because the first argument is nil? In green, it's asking me, is concatenation giving me nil because both arguments happen to be nil? Then I kind of generalize these, and I conjecture the lemmas on the right. And of course, in that case, some of them hold, some of them don't hold. I discard the ones that don't hold, and I keep the ones that do. Simple stuff, but quite powerful. So let me go back to this proof that we wanted to show that addition is commutative. So if you remember the definition of addition somewhere, this would be what we want to prove. The proof will always start with 4 things. So we have the goal, the typing context, the equalities, and inequalities. For the sake of the proof, we will discard the typing context until it becomes relevant, and we will just look at the equalities and inequalities. Sometimes I might say disequalities instead of inequalities, but that's just, there's 2 conflicting terms. It's random. The first thing we do is we actually, let me go back, we do not prove this claim. We do not prove that addition is commutative. We rather unfold the definition and then we prove. This is kind of important. I'll tell you a little bit why later. The first part of the cycle, which you'll see on top, is that we first do case analysis. So Propel, the inductive theorem prover, sees that there are 2 case expressions on either side. And it just explores the 4 possibilities of the branches. And these are the 4 possibilities on top. And then, essentially, to complete the proof, you have to prove every branch. If you focus on this particular branch, just to see what happens, we can, so that's the focusing. Then we can apply everything that we know. In this case, we only know 2 things, which are these things in the green box right there, being the branches that we follow. We now apply the rewrite of, in which we follow the rules, and we end up with these 4 other ones. We also apply all the known lemmas. I haven't shown you these things, but here they are. So essentially, distributivity of successor and addition. And then we generate these things. Now, this is after only 1 step of going down the branch. This is way too much, because there's way many more steps later. So the question now is, which one do we pick? Which one look attractive? There we have to score the branches, so we have to conjure some sort of magic, or we can use a simple scoring function, which turned out to be quite easy. You can look at the paper for the details of this function, of how we actually score, and then we can talk about it later. And then we select the top n branches. In this case, this is the branch that we follow. Now you follow these, you apply the rewrites, the symbolic execution, blah, blah, blah. Then you reach this point, and here you have to use the inductive hypothesis. But we have no inductive hypothesis. We have nothing in the green. Except now the typing contexts come in handy because according to the typing context, addition is commutative. So we can create the induction hypothesis out of the type, apply it, and we're done. And is this induction? Well, according to Propel, yes, it is, but modulo some kind of well-foundedness check. But the thing is, it falls out of the type. Then you're done. So that would be about the really nice system, the simple lemma generation. But I want to go back to this disequalities, because I've told you these are important, and this is some of the insights we found. For that, I'll just quickly skim through the proof of the fact that successor distributes over addition. Again, we pattern match. We follow one particular case. In this case, there should be a contradiction. How do we know? Because we simply see that B is both 0 and not 0. For those of you who attended my eGraphs talk on Monday, you would have seen the proof, the much longer proof to deduce that this is a contradiction if we did not track the disequalities. Essentially, we would have to apply 5 or 6 sequences of rewrites until we get some sort of reflexivity. To get an idea of how useful these inequalities, disequalities are, we took this commutativity proof, we turned off inequalities, disequalities, plotted all of the terms that come out of them, and this is the picture, very beautiful picture, I must say, that we get. In red are all of the useless branches that you would get rid of if you keep disequalities. The green ones are all of the fresh terms or new terms that you would not have explored if you disabled disequalities. So keeping disequalities allowed us to explore more things, more potential branches that could lead to a simpler proof. And if we disable them, then we're stuck proving contradictory terms. That was one of the insights. Of course, we evaluated this because we have to have an evaluation. We took the piano numbers and bit vectors as a first step. We compared it against, well, we collected about 43 cases that we wanted to prove. We compared them against Hipspec and Zeno being inductive theorem provers, Cycle Q being a cyclic theorem prover, CVC5 and Vampire being SMT provers who are able to do induction. And then the two kinds of Propel, one with support for disequalities, the last one, and the one without, which is the previous to last. We performed better than all of them. Good for us. And in the case for disequality, we actually could not prove about 2 or 3 cases. In some other cases, such as the TIP benchmark, which is a benchmark for inductive theorem provers, their disequalities helped us to prove things faster, so we timed out on more cases. But we also did some more evaluation on divide and conquer algorithms, CRDTs, data flow engine operations, etc. All the juicy detail are in the paper with the numbers, because here we can put numbers, there's too many. In conclusion, let me just summarize the insights that we got, which is that disequalities are very helpful. Please include them. Induction, well, your system is simpler if induction just falls out of it without having a special rule for it. The simple kind of conjecturing lemmas goes a really long way. Do not unfold definitions, just one layer is good enough in our case. And if you ever want to use progress, just make sure you only use the lemmas and the things which you have proven. You can use our tool. This is the website, and this is the concluding slide. If I may suggest a drinking game for you, every time you try to prove a simple thing using cock or lean or something, then please come to me. I'll give you a coaster for a glass, for like a shot glass, and then please take a shot every time you do that. It could be water. It doesn't have to be alcohol. Thank you very much, PLDI finishers. Enjoy your trip back home.
Okay, thank you for the talk. Very nice work. Do we have a question from the audience? Please go to the microphone.
And so, very cool project. Seems really interesting. I had a chat also with Guido and a short conversation about how you're planning to use eGraphs. Yep. And so I'm trying to do a very similar thing, right? But I haven't yet found what is an underlying logic to have this sort of like equational, symbolic only algebraic reasoning. So do you have an underlying logic?
In the paper, yes. So we have a really large formalism section.
Okay.
That is also simple, I must say.
And what kind of logic, more or less, is it?
Well, it's kind of simple constructive logic based on type theory.
Okay, yeah, it's very simple, like Hilbert style.
Kind of, yeah.
Yeah, thanks. Very interesting. I was curious about this lemma generation and exploration. How does that relate to Knuth-Bendix? Is it basically the same, or is it more or less expressive?
I think the generalization is actually pretty related. It might be more or less the same. Some older work explored this idea, and this generalization we kind of got more inspired from Zeno, which does something similar.
Okay, thanks.
Thank you.
Hi. So it seems like the examples you showed were properties that held across all of the total range of the inputs. Have you considered perhaps like a refinement system where a property holds for, say, half the domain of like the integers or something?
That's a very cool question, and I will give you the cool answer, which is that no, we have not. But since maybe something I should have mentioned is that we target just purely functional subset of Scala.
Mm-hmm.
And in my humble opinion, I think most of these refinements could be done via types. Mm-hmm. And then you can use some tools, which we actually saw in some talks about getting rid of these intermediary layers and data structures to kind of encode via your data type the refinement that you want, and then you kind of prove it over there.
Right.
Nonetheless, I still think there could be something that we could do inside of here. I just have to think about it.
Okay, yeah, thank you.
Yeah, thank you.
So a little bit along the same line, you might have an operator that is associative. It has a free identifier in it, but the associativity depends on some property of that free identifier. Is that possible to use in your tool?
I have a slide for this. I hope. Yeah, so I think maybe I hope this is something related. Let's see. So here I kind of show that addition is commutative associative. Then I kind of have this higher order operator called it's this thing. Zip with, which does kind of pairwise some kind of operation. And because these annotations are attached to the types, you're able to carry them around via higher order stuff. So for example, here in this zip with, I'm saying it's a function that takes a commutative associative idempotent function, then it lifts it up to another commutative associative idempotent function over the lists. Is this related? Was this okay?
I guess yes.
All right, thank you very much.
I'll also make
Yeah.
well, I was going to ask a similar question to the last two, but maybe it'll turn into more of a comment, which is you mentioned in the very beginning these applications to, for example, distributed data processing or stream processing where you may need commutativity and associativity. And in that context, some previous research found that sometimes you have a commutative associative operator, for example, for MapReduce, but it's only commutative associative, assuming some extra properties on the input. So I think that goes back to the previous question, would be a very, very interesting thing to consider in your setting.
Yeah, which is why I kind of lured you with the free advertisement of the paper so that you can give me these examples and I can try to formalize them myself. Thank you very much.
Okay, very good. So do we have any other questions from the audience? If not, thank you all for sticking around for the last session, and let's thank our speaker.